Welcome back to our Engineering Explainer series. I'm your principal engineer here at Durga Analytics, and today we are unlocking the absolute fundamental language of software scalability. Look, if you want to build systems that don't just work locally on your laptop, but actually survive contact with millions of real users in production, you absolutely have to master what we're covering today. It is a real game changer.
Just as a quick refresher on our overall programming and software engineering journey, we're building your expertise across 180 chapters and 9 modules. We've totally conquered Module 1's developer tooling, and you know our end goal is full-stack web, enterprise architecture, and Module 9's blockchain mastery. But today we officially enter Module 2, data structures and algorithms, kicking things off with Chapter 21. We're diving into the very heart of computer science to understand complexity.
So picture this. You've got two programs that both sort a list of names. On your tiny little test list of 10 items, they both finish instantly, right? They seem equally good. But out there in your real application with 10 million users hammering your servers, something drastically changes. Suddenly, one program finishes in a single second and the other takes a grueling hour. They looked identical on small inputs, but they're literally worlds apart under real load. The difference here isn't raw machine speed, it's how each program's cost grows as the input gets bigger.
Today's explainer is going to show you exactly how to prevent that massive production crash. Our roadmap: the question of scale, time versus space, core complexity classes, analyzing real code, designing for the worst case, and finally, nailing those interviews. Okay, let's jump right into Part 1, the question of scale and understanding growth. The difference between those two sorting programs we just talked about is what we call complexity. It's the shape of how the cost increases as your input gets bigger. Notice this really vital shift in our engineering mindset. We no longer ask, well, how long does this take? Because honestly, that depends on your hardware, the programming language, or even random background processes. Instead, we ask, how does the time grow as the input gets bigger? That question gives us a clean, objective, machine-independent answer.
Moving right along to Section 2, let's talk about time, space, and the actual engineering trade-offs.
Time complexity measures how fast your execution speed grows. If doubling the input roughly doubles the time, okay, that's one kind of growth. But if doubling the input quadruples the time, that is a much, much worse situation. Then we have space complexity, which measures your extra memory consumption. And real systems engineering is all about trade-offs, right? Often, you're deliberately trading one for the other, like burning some extra memory to cache data so you can massively speed up your time complexity.
We measure these growths using Big O notation, representing our input size as n. Big O focuses on the dominant growth as n gets huge, intentionally dropping exact constants. It's exactly like planning a road trip. If a buddy asks how long the drive is, you don't say, oh, it'll be 4 hours, 17 minutes, and 12 seconds. You just say, it takes about half a day. You give the order of magnitude because that's what actually matters for planning. If an algorithm takes 3n plus 5 steps, those numbers 3 and 5 are completely irrelevant to millions of records. We just call the whole shebang ON.
Let's hit Section 3. This is where we visualize performance by looking at the core complexity classes.
Now, looking at growth curves is super revealing. The horizontal axis is your input size and the vertical is your cost. Notice how beautifully flat that constant O of 1 line is at the bottom? Right above it, O of log n grows incredibly slowly. But as we move up to linear, O of n, and O of n log n, that incline gets noticeably steeper. And finally, check out that terrifying spike at the top, O of n squared. That right there? That's exactly what takes down production servers in the middle of the night. Let's do a quick rundown of the heavy hitters you'll see every day. O1 is constant. It takes the same time for 10 items or 10 million. It's the holy grail. O log n is logarithmic. Every time your input doubles, the cost only bumps up by a single step, which is just fantastic for scale. On is linear. Double the input, double the work.
ON log n is slightly worse than linear, pretty standard for efficient sorting. But down at the bottom, ON squared. 10 times the input means 100 times the work. That's a massive bottleneck waiting to happen.
Next up, Section 4. Let's actually analyze real code growth and read it like an architect. Finding an algorithm's big O just means looking at how its repeated work scales with the input size. And we have some incredibly reliable cheat codes for this. A fixed number of steps with no loops, that's O of 1. A single loop over your data is O of n. But a loop inside another loop, where both are iterating over the input, that multiplies out to O of n squared. Oh, and if you're repeatedly having the problem space, like flipping through a dictionary to find a word, you're squarely in O of log n territory.
When you actually look at runnable Python code, these rules jump right out at you. A basic for loop passing over items? Simple, O of n. But if you nest a for loop inside another for loop, you've just multiplied the work. Bam, ON squared. Conversely, just grabbing the very first item from a list takes one step, whether the list has 5 items or 5 billion. That's a pure O of 1 constant operation.
Which brings us to Section 5, designing for the worst case to protect your system. Here's a pro tip. When we state a big O, we almost always mean the worst case scenario. You might wonder, why not the average case? Well, because when you're building an enterprise architecture, hope is absolutely not an engineering strategy. An algorithm that's usually lightning fast, but occasionally catastrophically slow, is a ticking time bomb for system stability. That worst-case guarantee is exactly what protects your infrastructure from cascading failures under heavy load. Finally, Section 6. Let's tie all of this back to whiteboard interviews and daily engineering reality.
Whether you're sweating it out in a high-stakes interview or defending your architecture review at work, you have to be able to state and justify your complexity. If someone asks you to make a system faster, your goal is deliberately jumping to a better complexity class, like swapping an O of n squared brute force approach for an elegant O of n hash table. Don't fall into the trap of micro-optimizing small constants while ignoring a terrible growth shape. That said, in pure engineering reality, keep in the back of your mind that on extremely tiny inputs, constants can occasionally matter, but big O is what predicts your scale.
Now that you've got the exact vocabulary to predict scale, I want you to ask yourself, is there an ON squared nested loop silently hiding in your production code right now just waiting for the database to grow large enough to break it? Think about it. Master this framework today because in Chapter 22, we are going to apply this exact logic to master our first core data structure, arrays and dynamic arrays. It's going to be great, and I will see you there.
Welcome back to our 180-chapter software engineering journey. I'm really excited to dive into today's explainer with you. As a principal engineer here at Durga Analytics, I've spent decades building, shipping, and scaling real software systems. And honestly, my goal today is to help you do exactly the same. But before we get deep into the code and the architecture, let's quickly reorient ourselves on the roadmap, just to see exactly where this fits into your wider craft as an engineer. So our complete journey spans 9 modules. We go from developer tooling and computer science foundations, right through core languages like Python, Java, C, and C++, all the way into full-stack web development, enterprise app engineering, and even blockchain. Right now, we've just wrapped up Module 1's tooling foundations, and we're stepping firmly into Module 2, data structures and algorithms. This is where we really start dealing with the challenges of how code actually scales in a production environment. Out in the real world, whether you're building back-end microservices, optimizing a front-end interface, or designing massive enterprise architecture, your choice of data structures basically dictates your system's performance. I can tell you firsthand from the trenches, deeply understanding these core structures is literally what separates code that scales beautifully to millions of users from code that just crawls and crashes under pressure. Today, we're starting with the absolute foundation, Chapter 22, Arrays and Dynamic Arrays. In today's whiteboard session, here's our agenda. 1. Anatomy of an array. 2. Superpower random access. 3. The cost shifting items. 4. Fixed versus dynamic arrays. and 5 real-world engineering and interviews. All right, Section 1, Anatomy of an Array.
Before you can use an array effectively in Python, Java, or JavaScript, you really need to understand what an array is under the hood of the machine. By definition, it's the simplest way to store a collection of items. But the crucial point isn't how it looks to you in your code editor, it's the physical memory layout. An array stores items in a single, unbroken block of contiguous memory. Think of it as a row of slots, laid out one after another, each holding one item, accessed by a position number we call an index, which always starts at 0.
If you visualize those items, say the letters A through E, sitting right next to each other in this contiguous block, you'll notice there are absolutely no gaps. Because each item is the exact same size and they're packed perfectly together, every single slot has a highly predictable, calculable position number. Index 0 is your first item, index 1 is the second, and so on. This physical layout right here, this is the secret to everything that follows.
Which brings us to Section 2, Superpower, Random Access. This contiguous physical layout is exactly what gives the array its defining architectural superpower. It's why arrays are the undisputed workhorses of software engineering. Think of memory like a street of numbered houses. If those houses are perfectly ordered and equally spaced, you don't start at house 1 and knock on every single door just to find house 50, right? You know exactly where house 50 is based on the street layout, so you just walk straight to it. An array is that street. Because the computer knows the start of the block and the exact size of each item, it calculates the memory address of any index instantly. It doesn't search, it calculates.
So the major takeaway here is this. Accessing an array element by its index is an O of 1, or a constant time operation. Whether your array has 10 items or 10 million items, jumping directly to an index takes the exact same tiny fixed amount of time. This is random access. Whenever you're building an application and you know the exact position of the data you need, an array is going to fetch it for you instantly.
Let's move to Section 3, the cost, shifting items. In software engineering design, nothing is free. Every architectural choice has a trade-off. So we have to look at where arrays will absolutely hurt your app's performance if you're not careful. Remember how arrays required that unbroken, contiguous block of memory? Well, what happens if you want to insert a new item right in the middle, say at index 1? You can't just drop it in without overwriting what's already there. To make room, while strictly maintaining that contiguous block, every single item from index 1 onward has to be physically shifted one slot to the right. And if you're removing an item, the reverse happens. Everything shifts left to close the gap.
This shifting penalty is incredibly severe at scale. Inserting or deleting an item in the middle of an array costs O of n time. That means the cost grows linearly with the number of items that have to move. If you shift 1 million records in your database just to insert one row, your application is going to crawl to a halt and you'll probably be fielding a panicked call from DevOps at 3 a.m. Recognizing this cost profile is an absolutely fundamental engineering habit.
Section 4, Fixed versus Dynamic Arrays. Let's see how this actually works in modern programming environments. A classic array has its size permanently locked in the exact moment it's created. That's a massive problem if you're dealing with dynamic user data where you don't know your limits up front. So we have two types. Fixed-size arrays are rigid. If you say it holds 10 items, it holds 10, period, no more. But in modern production code, whether you're using Python's list, Java's array list, or JavaScript arrays, the solution we rely on is the dynamic array. Dynamic arrays give you this neat illusion of infinite space by automatically growing behind the scenes whenever they run out of room. Here's exactly how that magic works underneath. First, your dynamic array fills up its current memory block. Second, the system quietly goes to the operating system and allocates a brand new, bigger memory block, typically double the original size. Third, it copies all the existing items over from the old block to the new one. Now, that copy operation is O of n, so yeah, it's expensive. But once it's done, step 4 kicks in, and it just continues appending items as usual into the newly freed space.
Which takes us to Section 5, Real-World Engineering and Interviews.
Now that you understand the underlying mechanics, let's connect this back to your daily job shipping enterprise code and honestly, the traps that interviewers at top tech companies absolutely love to set. You'll want to internalize this operations matrix for the rest of your career. Access by index, that's O of 1. Searching an unsorted array, O of n, because you have to check every item. Middle insertion and deletion are O of n due to that shifting penalty we just talked about. And appending to the end is what we call amortized O of 1. When you're designing systems, you're constantly weighing that O of 1 access superpower against the O of n modification penalty.
And that brings us to a classic interview test. An interviewer will ask, if a dynamic array has to do an O of n copy when it resizes, how on earth can appending be considered O of 1? The model answer here is explaining the word amortized. Because the array doubles in size during a resize, those expensive O of n copies happen incredibly rarely. Averaged out over thousands of cheap O of 1 appends, the cost per append remains a constant, amortized O of 1. It's effectively constant in practice, which is exactly why adding to a Python list feels instant.
But what if an interviewer flips the script and asks, when should you not use an array? The biggest trap to avoid is treating arrays as the perfect solution for everything. The correct architectural answer is that you avoid arrays whenever your system's workload is heavily dominated by inserting and deleting items in the middle of a dataset. If that's your primary operation, the ON shifting penalty will absolutely destroy your application's performance.
Recognizing exactly when an array fails perfectly sets up our transition into Chapter 23, where we'll meet linked lists. A linked list is a data structure that flips these exact trade-offs right on their head, sacrificing instant access to give you blazing fast insertions. So as you head back to your development environments today, I want to leave you with one final, provocative thought. If your current code base is slowing down, are you absolutely sure you aren't silently shifting millions of array elements in the background without even realizing it? Think about it. Double-check your code, and I'll see you in the next explainer.
Hey everyone, and welcome. I'm a principal software engineer here at Durga Analytics. With a couple decades of experience building, shipping, and scaling real software systems and teaching engineers how to do exactly the same, I am absolutely thrilled to guide you through this explainer on Chapter 23, Linked Lists. Now, as a quick reminder, our entire programming and software engineering track is a massive, sequenced journey across 9 modules and 180 chapters. We go from foundational developer tooling in Module 1 through the core languages like Python, Java, and C++, right into full-stack web, enterprise architecture, and finally a deep dive into blockchain in Module 9. Today we're hitting a really pivotal moment in that journey. We're taking raw computer science theory and translating it into the actual practical engineering decisions you're going to make on the job. So just to give you a quick bearing on exactly where we are right now, we are deep into Module 2, which is data structures and algorithms. We're officially moving away from the foundational tools we set up in Module 1, and we're getting our hands dirty with how we actually lay out memory to scale real-world enterprise apps and decentralized systems. You know, back in Chapter 22, we explored the array. Well, today we're looking at its exact structural opposite. Okay, let's dive right into this. Here are the engineering specs we'll be covering today to understand those direct operational trade-offs. First, scattered memory. Second, the cost of traversal. Third, the power of rewiring. Fourth, singly versus doubly linked. Fifth, production trade-offs. And finally, our capstone connection. All right, Section 1, Scattered Memory. If you recall from our last chapter, an array is pretty strict. It keeps its items in one rigid, contiguous block of memory. And honestly, that rigid block is exactly what forces all that expensive data shifting when you want to insert a new item right in the middle. Linked lists, on the other hand, take a completely different architectural approach. They literally scatter their items anywhere they can fit in memory. But because they're scattered all over the place, they need a reliable way to find each other. So the core building block we use here is called a node. A node really just holds two distinct things: the actual data value, like maybe a user ID or a transaction amount, and a pointer. The entire structure starts from the very first node, which we call the head, and cascades down the line from there. Let's define that critical term, because it's absolutely crucial. A pointer, or a reference, is simply the location of another node. It literally tells the computer, hey, the next one is over here. Pointers are the absolute bedrock of memory mapping and software engineering. By following these pointers, starting right from the head and going node by node, you can traverse the entire sequence. And that works perfectly, even though the data isn't sitting physically next to each other in the hardware memory. Eventually, you hit the final node. Its pointer points to absolutely nothing, usually called null, which is just the system's way of marking this definitive end of the sequence. And this brilliantly illustrates the fundamental difference using a real-life analogy. Think of an array like a numbered row of post office boxes. If you need box number 5, you just walk straight up to it, right? Instant access. But a linked list? A linked list is basically a treasure hunt. Each clue, which is the node, holds a prize, your data, and tells you where the next clue is hidden, the pointer. You absolutely must follow the trail from the very start. There's no way you can just skip to the 5th clue without visiting the first 4. Moving on to Section 2, the cost of traversal. In engineering, every single architectural decision has a computing budget. For a linked list, that worst-case budget is big O of n. Because nodes are scattered and only reachable through a continuous, unbroken chain of pointers, accessing an item by its specific position means you might literally have to walk the entire length of the list. So, to get the millionth item, you have to read through the first 999,999 items first. This lack of random access is definitely the linked list's greatest weakness. It is the exact opposite of the array's superpower, which gets any index in O of 1, constant time. If you're building an application, maybe a snappy front-end dashboard or a heavy data analytics backend, and the operational profile constantly asks, give me item K, choosing a linked list is a really poor architectural decision. For sure, it will bottleneck your system at scale. Let's move to Section 3, the power of rewiring. So the crucial point is, why do we even use them? Why would we ever tolerate O of n access times in professional production software? Well, we tolerate it because of an amazing counterstrength: zero shifting. Remember the pain of arrays? If you insert data into the middle of a massive array, every single item after it has to shift over in memory, and that costs O of n time. With a linked list, if you want to insert a new node, let's call it new, between node A and node B, you literally just rewire 2 pointers. You point A to new and new to B. That operation takes O of 1, constant time. It doesn't matter if the list has 10 items or 10 billion items. You're just updating 2 memory addresses, and you're done. But wait, here is the critical distinction. And honestly, it's something I see trip up junior developers all the time. The rewiring itself is O of 1, yes, but that only applies if you are already at that specific spot in the list. If your system first has to search from the head of the list just to find where to make that insertion, well, that search is O of n. The magic O of 1 insertion speed is really only realized when you are already iterating through a dataset and making dynamic insertions or deletions as you go, meaning you are inserting at a known position. Let's move to and see how this builds in Section 4, singly versus doubly linked. In production environments, we generally see 2 main flavors, and they represent a strict engineering trade-off. In a singly linked list, each node points only forward to the next node. It is highly memory efficient, but the catch is you can only ever walk forward. In a doubly linked list, every single node stores 2 pointers, one pointing forward to the next node and one pointing back to the previous node. By doubling your pointer memory footprint per node, you gain the massive flexibility of 2-way traversal, which makes certain deletions and navigations so much easier. Actually, many real-world operating systems and enterprise applications default to doubly linked lists for exactly that flexibility. They're willingly trading a little bit of memory for a whole lot of utility. All right, Section 5, Production Trade-offs. Now, what's really interesting about this is where we shift from raw mechanics to how we actually make architectural choices in our day-to-day jobs. Looking at these contrasting profiles side by side, the general rule of thumb is this. Choose an array when your workload desperately needs fast access by position and mostly involves reading data or just appending stuff to the very end. On the flip side, choose a linked list when you're doing heavy insertion and deletion at points you're already tracking and you rarely, if ever, need random access. Neither tool is universally better. The true art of software architecture is simply matching the tool's cost profile to the job's specific requirements. And as someone who has interviewed literally hundreds of engineers, let me act as your mentor for a quick second and warn you about the top traps. First off, never, ever declare an array or a linked list universally better. Doing that just proves you don't fully grasp the trade-offs. Second, when you're asked why array access is faster, don't just blindly quote big O numbers. Explain the physical memory layout, contiguous versus scattered memory. That shows deep fundamental systems understanding. Finally, never say linked list insertion is always O of 1 without explicitly adding that at a known position caveat. Real engineering judgment is all about reasoning through these nuanced costs. Finally, Section 6, Capstone Connection. Let's connect this micro-level data structure to the macro-level systems we'll be building later on. The pointer logic you learned today, it doesn't just stop at simple lists. It is the exact same foundation we're going to use for complex data routing later in the track. When we get to trees in Chapter 26 or graphs in Chapter 29, we're basically just taking nodes and references and arranging them differently. When you build full-stack enterprise applications or map out decentralized blockchain ledgers in Module 9, you are relying entirely on the mental models of pointers and scattered memory that we just locked in today. It's a real game changer. So we've mastered the array's contiguous speed and the linked list's rewiring superpower, but what happens when our systems demand strict rules on who gets processed first? Now that we have arrays and linked lists, how do we build structures that strictly control the order of data? Well, I'm going to leave you with that provocative thought because answering it is exactly what we are going to do in our next explainer chapter, Chapter 24, Stacks and Queues. I'll see you there. Hey everyone, and welcome back to the explainer for Chapter 24. I'm your host, and as a principal software engineer here at Durga Analytics, where I've spent decades building, shipping, and scaling actual real-world software, I am super excited to guide you through this material. Today, we're taking the foundational computer science concepts of stacks and queues and translating them straight into professional software engineering practice. We are moving way beyond the textbook today. We're going to see exactly how these structures power the massive enterprise applications and developer tools you use literally every single day. But first, let's quickly ground ourselves in the bigger picture. As you know, our overarching programming and software engineering journey is a massive one. 180 chapters spread across 9 modules, taking us all the way from foundational developer tooling to full-stack web, enterprise architecture, and even a blockchain specialization. Right now, we're deep into Module 02, Data Structures and Algorithms. You've already conquered the basics of arrays and linked lists in the last couple of chapters. Well, today we are mastering 2 deceptively simple structures that are built directly on top of those foundations. And trust me, these are the engines that will ultimately drive everything from our core languages to complex full-stack apps. So here is our roadmap for today's explainer. First, we'll tackle stacks and the LIFO principle. Second, queues and FIFO. Third, we'll pop the hood and look at the underlying architecture. And finally, we'll wrap up with some interview prep and next steps. All right, let's dive right into Section 1, stacks, last in, first out. Okay, so what exactly is a stack? It's really a deceptively simple collection, defined entirely by one incredibly rigid rule. You only ever add to and remove from one single end. We call that end the top. Think of a physical stack of plates in a busy cafeteria. You add a clean plate to the top of the pile, an action we call a push, And when you need a plate for your food, you take it directly from the top. We call that a pop. You wouldn't try to yank a plate from the middle or the bottom, right? You'd bring the whole pile crashing down. Because the last plate you put on is the very first one you take off, we call this a last in, first out structure, or LIFO for short. And honestly, the sheer simplicity of just pushing and popping from that single end, that's exactly its greatest superpower. In actual production engineering, stacks are literally everywhere once you know what you're looking for. A good rule of thumb: whenever an engineering problem has a most recent first or reverse order kind of flavor, a stack is usually your best friend. For instance, the undo feature in your favorite text editor, that's just a stack. Every time you type, it pushes the action. Hitting undo just pops the most recent action right back off. Then, of course, there's the call stack, which is literally the mechanism that runs your programs and generates those stack traces we talked about back in Chapter 16. We also use stacks heavily for bracket matching in code compilers, and they are the core engine driving depth-first graph traversals, which we're going to dig into later in Chapter 30. Moving right along, let's check out Section 2, Queues, first in, first out. So if you totally get the stack, grasping the queue is super easy. You basically just flip the script. Instead of a stack of plates, think of a fair line at a retail checkout. A queue enforces a first-in, first-out rule, or FIFO. Items are added to the back of the line, which we call in-queuing, and they are processed and removed from the front, which is dequeuing. It's perfectly fair. The very first item to arrive is absolutely the first one to leave in its exact arrival order. Absolutely nobody gets to jump the line. So where exactly does this fit into our wider craft as software engineers? Well, whenever your system architecture demands a sort of wait-your-turn fairness, a queue is your essential go-to tool. If you're building a massive server task processing system, incoming requests wait in a queue. Printer buffering, asynchronous message brokers handling millions of events in enterprise apps, job scheduling. These are all completely powered by queues. Plus, if you ever need to explore a network or a data tree level by level, a queue is the exact structure that drives that breadth-first traversal. It just perfectly models that concept of processing in arrival order. All right, now for the really fun part, Section 3, Architecture, Under the Hood. Look, knowing what these structures do on paper is one thing, but as engineers who actually ship real software, we have to understand how they are built deep down inside our systems. We've seen the behavioral contrast, right? Stacks restrict data access to a single end for both push and pop to give us that LIFO behavior. Queues, on the other hand, orchestrate traffic across two different ends, and queuing at the back, dequeuing at the front to create FIFO behavior. But the real million-dollar question for a system builder is this: where does the actual data live? And that brings us to a crucial architectural lesson. Honestly, this might be the most important takeaway of the entire explainer. Stacks and queues? They aren't rival brand new storage mediums competing with the arrays and linked lists we just learned about. Not at all. They are high-level behavioral wrappers built directly on top of those simpler foundations. You can build a stack using a dynamic array, where a push is literally just a simple append operation. You can build a queue using a linked list by just maintaining pointers to both ends. The underlying storage itself doesn't define them. Their strict access rules do. Because we enforce these incredibly strict rules, restricting our operations to just the very ends of those underlying arrays or linked lists, we get a massive performance payoff. There is zero searching involved. You never, ever iterate through a stack or a queue to find an element. Because of that, every single push, pop, NQ, and DQ executes in blazing fast, constant O1 time. The computational work is a fixed, tiny amount, whether the structure holds 10 items or 10 million. That ruthless efficiency is exactly why they are totally ubiquitous in scalable software systems. Let's bring it all home with Section 4, Interview Prep and Next Steps. So, being able to recognize when a really complicated-looking problem actually just boils down to a simple O1 stack or queue, that is a remarkably high-value skill. It's a pattern matching ability that top tech companies aggressively test for in coding interviews. Let's look at a classic whiteboard scenario. Imagine a senior interviewer asks you to write code that validates if the brackets in a string of source code are perfectly balanced. What structure helps here? And more importantly, how do you handle mismatched types? Like, say, a square bracket attempting to inappropriately close a standard parenthesis. Let's walk through the model answer so you can see how to build a bulletproof solution here. The secret weapon is a stack. The algorithm is surprisingly simple. Just push every single opening bracket you see onto the stack. Then, whenever you encounter a closing bracket, you pop the top of the stack to verify it's an exact matching pair. Once you reach the end of the string, you just confirm the stack is entirely empty. Done. Now, here's the trap that so many candidates fall into. They try to solve this by simply keeping a running count of open and closed brackets. Simple counting completely fails on mismatched types. Think about it. An open parentheses, followed by an open square bracket, and then a closed parentheses. Counting says, hey, we have 2 opens and 2 closes, we're good. But the order's totally corrupted. A stack's LIFO nature perfectly, elegantly enforces that required order. And with that, we have officially conquered Chapter 24. You can now confidently explain stocks and queues, their O1 operations, the mechanics of LIFO and FIFO, and, most importantly, you've sharpened your engineering instinct to know exactly when a production problem demands them. But I want to leave you with one final provocative thought. We have just mastered the rigid access rules of sequential, ordered data structures. But what if we don't care about order at all? How on earth do we architect lightning-fast data lookups when we just want to find one specific piece of data instantly out of millions without searching? Well, we are going to architect exactly that in our next explainer on Chapter 25, hash tables, as we wrap up the core structures of Module 02. It's going to be a great one. I'll see you there.
Hey everyone, welcome back. We are now on Chapter 25 of our 180-chapter programming and software engineering journey. I'm a principal engineer here at Durg Analytics, and with decades of building, shipping, and scaling real software systems, I am super excited to guide you through this next topic. Just to orient us, we're in Module 2 of our 9-module curriculum, focusing on data structures and algorithms. Today, we are conquering the final and honestly the most crucial linear structure in your toolkit, hash tables.
Here's our game plan for today. We're going to look at the O of n search problem, unpack how hash functions solve it, figure out how we get that sweet O of 1 lookup speed, what to do about collisions, and finally, why this data structure is your absolute best friend in tech interviews, before wrapping up with our key takeaways.
All right, Part 1, the O of n search problem. Let's start with a massive scaling bottleneck that you are quite literally guaranteed to hit in production.
Imagine you've got 1 million users in your application's database. You need to pull up one specific username, like right now. If you're relying on an unsorted array, that's an O of n operation. You're forced to check every single entry one by one until you find a match. Now, when your app scales to millions of concurrent real-time requests, that O of n scan is going to completely tank your servers. It's just not an option. You need a data structure that jumps straight to the exact location using just the username. A hash table bridges this exact gap, giving you that location instantly an O of 1 time.
Moving on to Part 2, the hash function solution. So, how do we actually pull this off? How do we magically get from an arbitrary string like a username to a direct memory index?
It's all about key-value pairs. You probably use these every single day without thinking about it, whether it's Python dictionaries, Java maps, or caching layers like Redis. The beating heart of this entire structure is the hash function. It takes your lookup key, like our user's name, and mathematically converts that string into a specific integer. That integer corresponds to a physical storage location, usually called a bucket or a slot, inside an underlying array.
This brilliantly illustrates the actual mechanism. Notice how you never actually search the array. Never. Instead, you take a key like Alice, run it through the hash function, and bam, it tells you exactly which bucket her data lives in. Let's say it computes to slot 3. Storing and retrieving work exactly the same way. Because the exact same key will always hash to the same exact slot, you just compute the location and jump right to it. Zero searching required.
Part 3.
Achieving O of 1 lookup speed. Let's really dig into this headline feature and see why it's such an engineering game changer.
Think of it like a real-world code check at an event. When you drop off your jacket, you don't go searching every single hook in the building, right? You hand the attendant your coat. That's your key, and they hand you a numbered tag. When you come back to get it, they look at the tag and go straight to your coat, instantly, because the hash function computes the array slot directly, and grabbing an item by a specific index in an array is an O as 1 operation. Looking up, inserting, or deleting an item is O as 1 on average. It literally takes slow, linear searches and makes them essentially instantaneous, no matter how much data you throw at it.
Now for part 4, handling collisions with chaining. Because let's be real, production software is messy, and we have to talk about what happens when two totally different keys output the exact same slot number.
A hash function takes a massive, essentially infinite amount of possible keys and maps them into a limited, finite number of array slots. So eventually, you are going to have two keys that point to the same number. We call this a collision. If we don't plan for this, our worst-case lookups are going to start degrading right back toward O of n speed, which completely defeats the purpose. Our hash table has to handle these collisions gracefully to maintain peak performance.
The most common workaround here is a really slick technique called chaining. Notice on the slide how, instead of holding just one piece of data, each slot actually holds a tiny linked list. This means if keys like Alice and Alex both happen to hash to slot 3, they just share that slot by linking together, without overwriting each other. As long as your hash function is doing its job and spreading keys out evenly, these lists stay super tiny, and your lookups stay effectively O of 1.
Part 5. The Interview Power Tool. Let's connect all this to your career and see why this data structure is considered the ultimate weapon for tech interviews at top-tier companies.
I am not exaggerating when I say the hash table is one of the most powerful tools in your entire engineering toolkit. Take the classic two-sum interview problem, where you have to find if two numbers in a list add up to a specific target. The brute force approach uses nested loops to check every single pair, which takes a painfully slow O of n squared time. But if you utilize a hash table, you can solve it in a single O of n pass. You're intentionally trading space for time. You just iterate through the list once, throwing the values you've seen into a hash table, and constantly checking if the complement you need is already sitting in there.
The massive engineering mindset shift here is realizing that the question, "Have I seen this value before?" instantly becomes an O of 1 check. By instantly checking for a value's complement, you are demonstrating to interviewers that you know exactly how to deliberately eliminate nested loops and slash complexity. Recognizing when to deploy a hash table is absolutely a defining characteristic of a top-tier engineer.
Finally, Part 6, Key Takeaways and Next Steps. Let's lock in what we've mastered today as we close out the core linear structures in Module 2.
To sum this all up, you should now be able to comfortably explain how hash tables use key-value pairs. You understand that hash functions compute a direct storage location rather than making you search for it. You know that this is what gives us our blazing fast O of 1 average lookups, and you understand how chaining elegantly handles those inevitable collisions. Most importantly, you know when to actually use this tool in real production software to turn sluggish O of n bottlenecks into instant O of 1 operations.
At this point, we have completely mastered linear structures. Arrays, linked lists, stacks, queues, and now hash tables. You have the foundational tools for flat data and instant lookups. But what happens when our data isn't flat? What if it's hierarchical, like a file system on an OS, an enterprise org chart, or the DOM of a web page? A hash table really isn't going to help you much there. So, next up in our journey, we move to Chapter 26 to tackle trees and binary search trees. Until then, keep writing clean code and keep optimizing.
Hey everyone, and welcome to this explainer on Chapter 26 of Programming and Software Engineering. I'm a principal engineer here at Durga Analytics, and over the past couple of decades, I've been building, shipping, and scaling real production software systems. Now, in our previous chapters, we covered linear data structures, your arrays, lists, stacks, and queues, where all the data just sits neatly in a single line. But today, we're leaving those linear structures completely behind. We're diving into the architecture of trees, which is where we actually start modeling the complex, branching, hierarchical shapes of the real world. But before we start slinging any code, let's just do a quick reminder of our overall 9-module journey. We start with developer tooling, move into data structures and algorithms, then Python mastery, Java programming, C and C++, JavaScript and TypeScript, full-stack web apps, enterprise apps, and finally, blockchain and DLT. We are currently right in the thick of Module 2. You've already conquered the tooling, and now you're laying the absolute foundation for everything that follows. Trust me, the concepts we covered today, they're going to follow you all the way through those advanced languages, straight into enterprise architecture and our blockchain specialization. All right, so here is our explainer roadmap for today. We're going to cover Welcome to Chapter 26, the anatomy of a tree, the binary search tree property, the power of log n, the unbalanced tree trap, and finally, real-world engineering and interviews. Okay, let's jump right into Section 1. Welcome to Chapter 26, from lines to hierarchies. Moving on to Section 2, the anatomy of a tree, building the engineering vocabulary. So, like I mentioned, up until now, every structure we've built has been a straight line. But huge amounts of real-world data, think about a company org chart, a computer file system, or even the DOM of a web page, are intrinsically hierarchical. To build these, we actually borrow our vocabulary straight from a family tree. Though a funny quirk in computer science is that we draw our trees completely upside down. The root sits right at the very top. That's your single starting node with absolutely no parent. From there, it branches downward into parent nodes, which obviously have children below them. Nodes that share the same parent, we just call those siblings. Eventually, all this branching ends at the leaf nodes, the absolute tips of the tree that have 0 children. And honestly, under the hood, this whole shebang is built on the exact same pointer idea you already learned with linked lists. We're just branching outward instead of moving in one straight line. Now, here is a crucially important concept you need to grasp: height. The height of a tree is simply the number of levels. Basically, how far is it from that top root node all the way down to the deepest leaf? So why does this matter? Well, in production systems, this single, simple metric completely dictates your ultimate performance. The height determines the absolute maximum number of steps it's going to take you to get from the top of your data to the bottom. All right, Section 3, the binary search tree property, the decision engine. By restricting our nodes so they have a maximum of only 2 children, we create what's called a binary tree. This perfectly encodes simple yes or no, left or right decisions. But a plain binary tree isn't quite enough for us. We actually need to sort it to make it useful. Enter the binary search tree, or BST. When we apply the BST property to those binary decisions, we enforce a really strict ordering rule that turns a basic, boring tree into a high-speed searching machine. The rule is this: for absolutely every single node in the tree, everything in its entire left subtree must be strictly smaller, and everything in its right subtree must be strictly larger. And this brilliantly illustrates the engine in action. Take a look at the root node, which is 8. Everything to the left is smaller, everything to the right is larger. So, if we are searching for the number 6, we just follow the math. We start at 8. Well, 6 is less than 8, so we take the left branch down to 3. Now 6 is greater than 3, so we take the right branch, and boom, we found it. At every single node, you are literally discarding half of the remaining data. You don't even have to look at the vast majority of the nodes in the structure. Let's break down the actual algorithm here and see how this builds a predictable, repeatable loop for finding literally any value in the structure. Step 1. Compare your target with the current node. Step 2, if it's smaller, you go left. Step 3, if it's larger, you go right. Step 4, just repeat until you find it. This is exactly like doing a binary search on a sorted array, but we've built it directly into the pointer architecture of the nodes themselves. If you're implementing this in code, it translates beautifully to a super simple while loop in Python or a really clean recursive function if you're writing in Java. Which brings us to section 4, the power of log n, scaling to 1,000,000. In my decades of shipping actual systems, this is the exact moment where theoretical computer science becomes straight-up production-grade magic. We've talked about big O notation before, but this is where you really, truly feel its impact. If the tree is balanced, meaning the left and right branches are kept roughly even, that height we talked about is logarithmic. Because every single step halves the remaining data. Finding one single record among 1,000,000 items takes roughly 20 steps. Seriously, let that sink in for a second. 1,000,000 records, 20 comparisons. That gives us that wonderfully fast O of log n time for searching, inserting, and deleting. This mathematical reality is exactly why modern databases can query massive datasets in mere milliseconds. But of course, there's a catch. Section 5, the unbalanced tree trap, the production gotcha. And this is a massive catch that will completely break your production app if you aren't paying attention. You absolutely cannot just assume you're getting O of log n performance just because you instantiated a BST class. The performance is highly conditional. On the left side here, we have a perfectly balanced tree, yielding our beautiful lightning-fast O of log n performance. But what happens if you insert data into your tree that is already sorted? Say you insert 1, then 2, then 3, then 4. Because 2 is greater than 1, it goes to the right. 3 goes to the right of 2, 4 goes to the right of 3. You completely lose the branching. The tree becomes entirely unbalanced, and your blazing fast O of log n performance plummets to a sluggish, terrible O of n. Under these conditions, the tree essentially devolves into a slow, lopsided linked list. Instead of taking 20 steps to search 1,000,000 items, it could literally take 1,000,000 steps. This is hands down the single most important caveat to remember when you are designing systems with BSTs. That O of log n guarantee only exists if the tree remains nicely balanced. Let's tie this all together in section 6, real-world engineering and interviews, FANG fundamentals. This balance versus degenerate dynamic we just talked about, it isn't just academic theory. It powers real database indexes and the ordered sets, like Java's tree map, that you use in your standard libraries every day. And when you interview for a backend, full stat, or systems role at top companies, they will very often ask you this exact question. How would you check if a given binary tree is a valid binary search tree? They aren't just making small talk. They're testing if you truly understand the depth of this architecture or if you just memorized a few definitions. Now, a lot of junior developers completely fall for the trap here. They'll just write a function that checks if a node's immediate left child is smaller and its immediate right child is larger. But a real engineer knows that a node deep, deep down in the right subtree might accidentally have a value smaller than the main root of the entire tree, which completely violates the structure. To do this right, you actually must traverse the tree while carrying the full allowed minimum and maximum range down the branches with you. You tighten that range as you go left or right to verify deep structural validity. So if you take away absolutely nothing else from today's explainer, let it be this fundamental truth about performance and structural integrity. The O of log n depends on the tree staying balanced. It's not magic, folks. It's architecture. And as software engineers, our job is to ensure our architecture can handle whatever messy, real-world data throws at it without degrading into a crawl. And that leaves us with a rather huge engineering problem. If unbalanced trees destroy our performance and real-world data is very often partially sorted, how do we architect self-healing systems that force the tree to stay balanced no matter what crazy data we throw at it? Are you ready to let algorithms literally write their own structural rules in real time? Well, that is exactly the magic we are going to solve in our next explainer on Chapter 27, Balanced Trees and Their Trade-Offs. Thanks so much for joining me. Keep building, and I'll see you in the next one. Hey everyone, welcome back to The Explainer. I'm a principal software engineer here at Durga Analytics. And you know, Over the decades I've spent building, shipping, and scaling real-world software systems, one of my absolute favorite things is teaching you all how to do the exact same thing. Today, we're diving into Chapter 27 of our track, Balanced Trees and Their Trade-Offs. If you've ever wondered how standard libraries in Python, Java, or C++ keep data moving at literally lightning speed in production, well, you're in the right place. Let's jump right in. Just to quickly map out where we are in our journey, this explainer is part of our massive 9-module, 180-chapter programming and software engineering track. We go from Module 1's developer tooling all the way to Module 9's blockchain mastery. Right now, we're squarely in Module 2, data structures and algorithms, specifically Chapter 27. Remember that major cliffhanger we ended on in Chapter 26? We saw that a plain binary search tree is incredibly fast, but only if it stays balanced. If it doesn't, well, it completely collapses. Today, we're looking at the engineering fix for that. So here's our agenda for today. First, we'll look at the danger of plain BSTs. Second, the self-balancing guarantee. Third, we'll cover rotations and restoring balance. Fourth, we'll compare AVL versus red-black trees. And finally, we'll break down the overall engineering trade-off. All right, Section 1, the danger of plain BSTs, the hidden time bomb in your data structures. Listen, in real software engineering, we just can't afford surprises. Period. Relying on a plain binary search tree in a production environment, it's basically a ticking time bomb just waiting for an edge case. Think about it. A beautiful, perfectly balanced tree has a height of roughly log n. That means search times are blazingly fast. But here's the catch. Nothing in a plain BST forces it to stay that way. If you insert data that's already sorted, or even just nearly sorted, which, by the way, happens all the time in the real world, every new piece of data just hangs off to one side. You end up with this tall, lopsided chain. Honestly, at that point, it's basically just a really slow linked list wearing a tree costume. And this is exactly where the danger lies. When your tree degrades into a linked list, your search cost explodes. It goes from a super fast O log n to a brutally slow O of n linear search. Suddenly, the entire performance benefit of using a tree in the first place is completely gone. In an enterprise system, that kind of unpredictability is totally unacceptable. We simply cannot rely on getting lucky with our input data to keep our apps running fast. Hope is not a valid software architecture strategy, right? We need a rock-solid guarantee. Which brings us to Section 2, the self-balancing guarantee, engineering a structural solution. So, when the naive approach fails under real-world conditions, what do? We engineer a structure that fixes itself. A self-balancing tree is simply a binary search tree that automatically restructures itself to keep its height around log n as you insert or delete data. It does this by maintaining a strict invariant. Now, an invariant is just a condition that the data structure always promises to uphold. In this case, that promise is structural balance. By constantly monitoring and enforcing this invariant, the tree gives us a powerful guarantee. Your search, insert, and delete operations will always be O log n in the worst case. No matter what order the data arrives in, the system stays highly available. Moving on to Section 3, rotations and restoring balance. Let's look at the internal machinery of self-balancing trees. So how exactly does the tree magically fix itself without messing up all your sorted data? The secret is rotations. Now, as a principal engineer, I'll let you in on a little secret. You really don't need to memorize the rote mechanics of left and right rotations. Standard libraries are going to handle that implementation for you. But what you absolutely must understand is the concept itself. A rotation is just a small, localized reshaping. It pulls one node up and pushes another one down to even out the height. And it does all of this without breaking the fundamental binary search tree ordering. Here's the step-by-step logic happening quietly under the hood. First, you insert or delete a value. Second, the tree does some quick bookkeeping to check its balance condition, that invariant we talked about. Third, if it notices a subtree has gotten a bit too lopsided, it quietly performs a rotation to restore balance. It's kind of like an automated background maintenance job, constantly working to ensure your database index never, ever slows down. All right, Section 4, AVL versus red-black trees. Let's talk about the real-world implementations you'll see in production. When you're out there writing Python, Java, or C++, what self-balancing trees are actually running behind the scenes? Well, there are two major heavyweights you need to know: AVL trees and red-black trees. An AVL tree enforces a really strict balance. Because it keeps the tree as mathematically short as possible, your lookups are incredibly fast. The catch? It has to rotate aggressively to maintain that strictness, which makes inserts and deletes quite costly. Now on the flip side, we have the red-black tree. This uses a clever coloring scheme, literally tagging nodes as red or black, to enforce a much looser balance. Yes, it allows the tree to be slightly taller, meaning lookups might be a tiny fraction of a millisecond slower, but it does way less work during inserts and deletes. Because of this beautifully well-rounded performance profile, red-black trees are the absolute workhorses of the industry. They are the engine powering the ordered maps and sets that you use every single day. And that brings us to Section 5, the engineering trade-off. Why we gladly pay the performance tax. You know, my job isn't just knowing the syntax of a tool, it's weighing the trade-offs. In software, absolutely nothing is free. The trade-off with self-balancing trees is crystal clear. The cost? It's the extra compute cycles spent on all that bookkeeping and those rotations every time you insert or delete a node, plus the added complexity of the structure itself. But the benefit? You get a guaranteed ironclad O log n performance profile. We gladly pay this tiny performance tax up front because the alternative, a complete catastrophic system collapse down ON speeds just because a user uploaded sorted data, is totally unacceptable. Predictability at scale is always worth a minor overhead. Before we wrap this up, let's talk about how this applies to your career and interview prep. This specific concept comes up constantly in top-tier technical interviews. A classic question you'll hear is, why use a balanced BST instead of just a plain one? To absolutely nail this question, your model answer needs to highlight that a self-balancing tree restructures itself to guarantee worst-case O log n operations, completely regardless of the input data. But listen closely, because here's the trap so many candidates fall right into. They list the benefits, but they completely forget to explain why we even need that guarantee in the first place. You have to explicitly mention that a plain BST can silently degenerate into a super slow O of n linked list when it's fed sorted input. Understanding that specific failure mode, that is what demonstrates real senior-level engineering depth. To wrap up, I want to leave you with this core principle. All software performance guarantees rely entirely on maintained structural invariance. Whether you're dealing with a database, a load balancer, or a simple search tree, if you understand the invariant, you understand the system. Always ask yourself, under what condition does this hold true? Making that a habit is going to make you an elite engineer. But hey, what if you don't actually need to search for a specific value? What if you only care about finding the absolute maximum or minimum value instantly? Do you still need to pay the tax for a fully balanced tree? Well, up next in Chapter 28, we're going to dive into heaps and priority queues to answer exactly that. Thanks for joining me for this explainer, and keep building great software.
Hey everyone, and welcome back to The Explainer. I'm a principal software engineer from Durga Analytics, and you know, over the decades I've spent building, shipping, and scaling actual production software. There is nothing I love more than teaching other engineers how to do the exact same thing. Just as a quick refresher, this is all part of our massive programming and software engineering course, a real sequenced journey covering 9 modules and 180 chapters. We go from the absolute bedrock of developer tooling and computer science, right through core languages like Python, Java, C, and C++, all the way into full-stack web, enterprise architecture, and even blockchain. Right now, we're right in the thick of Module 02, tackling data structures and algorithms.
And today we are diving into Chapter 28, Heaps and Priority Queues.
Okay, let's kick things off by picturing a classic, real-world engineering scaling problem. Imagine you're building an emergency room triage system, or maybe an operating system task scheduler, or even a super high-throughput network router. In these kinds of dynamic systems, items are just constantly flooding in and popping out. And you continually, literally every microsecond, need to find the next best or most urgent item. So how do you actually do that without completely blowing up your compute costs by resorting the whole pile every single time? Because I'll tell you right now, if you get this wrong in production, your entire system just grinds to a halt.
So here's our game plan for today. We're going to cover 1. The next best problem. 2. The heap property. 3. Heap operations and a really cool array trick. 4. Building the priority queue. And 5. Real-world engineering and interviews.
All right, let's jump straight into part 1, the next best problem, and how we escape the dreaded O(n log n) trap. Whenever you're building a system that always needs to grab the absolute smallest or largest item, you really only have a couple of naive options to start with. First, you could just keep your entire list perfectly sorted. Sounds good, right? But here's the catch. Resorting your list after every single insertion or deletion costs O(n log n) time. In a system handling millions of events a second, that is vastly too expensive. Alternatively, you might think, okay, I'll just keep them all unsorted and scan through to find the minimum when I need it. But doing a plain scan takes O(n) time for every single request. Still too slow. Keeping everything perfectly sorted from top to bottom is a massive waste of resources when you really only need that one extreme item at any given moment. We definitely need a better way.
Which brings us nicely to part 2, the heap property, or, as I like to think of it, designing just enough order. To solve this, we use a specialized data structure built entirely for this one specific job. You probably remember trees from chapter 26, right? Well, a heap is a specialized binary tree with one absolute golden rule, the heap property. Let's think about a min heap for a second. The rule is super simple. Every parent node must be smaller than or equal to its children. So if you've got a node with the value 2 at the top, its children might be 4 and 7, and that 4 might have children like 9 and 5. Because every single parent is smaller than its children, if you trace that logic all the way up, the absolute smallest item, the 2, must inevitably sit right at the very root of the tree. Boom, it's instantly accessible.
Now you might be wondering, wait, how is this different from the binary search trees we just talked about? It's a great question. In a BST, you have a really strict left-right order. Everything left is smaller, everything right is larger. But in a heap, there is absolutely no left-right rule. You could have a 9 on the left and a 5 on the right of their parent, and that is totally fine. A heap only cares about the parent-child relationship. This much looser, just enough ordering is exactly why a heap is drastically cheaper to maintain under a heavy production load. We don't care about sorting the whole thing, we only care that the extreme value floats right to the top.
Let's move on to part 3. Operations and the array trick. Time to look under the hood.
As software engineers, we care deeply about big O time complexities, and this is where the heap gives us a massive engineering victory. If you just want to peek, check what the most urgent item is. It takes O(1) constant time. It's literally right there at the root. If you need to insert a new item, it takes O(log n) time. You just drop it at the bottom and kind of bubble it up, swapping it with its parent until that heap property is fixed. And to extract or process that top item, you remove it, grab a leaf from the bottom, stick it at the root, and sink it down into its proper place. That's also just O(log n) time. In modern practice, your standard libraries give you this out of the box, like heap queue in Python or priority queue in Java. Instant access, rapid updates. Problem solved. And honestly, this brings us to one of my all-time favorite systems optimizations, the array trick. Even though we mentally map a heap as this branching tree with nodes, in actual memory, it is almost always stored as a plain, flat array. Because a heap is always perfectly balanced and tightly filled in, you can just lay out its levels from left to right directly into an array. We covered the blazing O1 speed of arrays back in Chapter 22. By storing it this way, you figure out who is related to who using simple index math. For example, just multiply a parent's index by 2, and bam, you've found its left child. This means zero node objects and absolutely zero pointer overhead. It's an unbelievably fast, cache-friendly hack.
All right, Section 4, Building the Priority Queue and Serving by Urgency.
We talked about standard queues in Chapter 24. A standard queue is strictly first in, first out. It serves items purely by arrival time. Think of it like regular folks waiting in line at a coffee shop. But a priority queue, that is a whole different beast. It serves items based entirely on their urgency, completely ignoring when they actually arrived. If a VIP walks into our coffee shop, they don't wait, they jump straight to the very front of the line. Because a heap is perfectly designed to give you the highest priority item in O of 1 time and slot in new arrivals in O of log n time, it is basically the undisputed go-to backing engine for any priority queue.
Which leads us nicely to Section 5, Real-World Engineering and Interviews. Where do heaps actually ship?
You are going to see priority queues absolutely everywhere in enterprise architecture. They power OS task schedulers, making sure critical system processes grab CPU time way before your background downloads do. They handle massive event simulations, they manage network bandwidth routing, and they're heavily used in real-time streaming data for top K analytics. And hey, spoiler alert, this exact pattern is the beating heart of shortest path routing algorithms, which we are going to be building hands-on very soon in Chapter 37.
Because it's so universally useful, you are 100% going to encounter this in tech interviews. Here is an absolute classic trap they love to spring on you. Find the k largest elements in a massive array. A junior coder will usually just freeze or immediately suggest sorting the entire array and then slicing off the top k elements. But as we know, sorting the entire array takes O n log n time. As a senior engineer, your brain should instantly recognize this as a priority queue pattern. Here is the elegant, pro-level solution. You just keep a tiny min heap bounded to a maximum size of k. As you scan through that massive array, you check each element. If your new element is larger than the minimum element currently sitting at the top of your small heap, you just extract that minimum and insert the new guy. Once you finish scanning, that little heap holds exactly the k largest items. This bounded heap approach runs in O of n log k time, and crucially, it keeps your memory footprint bounded to just O of k space. It effortlessly crushes the naive sorting approach. Knowing when to pull this tool out of your belt is exactly what gets you the job.
So let's bring this all together. If you remember one thing today, make it this. Whenever your system requires you to constantly process the most urgent, the smallest, or the largest item next, you reach for a heap and a priority queue. This beautifully completes our mental map of trees. We've got the binary search tree for general left-right searching, the balance tree to guarantee that search stays fast, and now the heap, using parent-child ordering for instant access to the extremes. 3 highly specialized trees for 3 very distinct engineering jobs. But it makes you think, what happens when our data doesn't have a clear parent-child hierarchy at all? What if everything is just connected to everything else in one massive, chaotic web? Well, next up, we are leaving the rigid world of strict trees behind and diving headfirst into the highly interconnected world of networks. I'll see you in Chapter 29, Graphs and Their Representations.
Hey everyone, and welcome back to another explainer from Durga Analytics. I'm your host, and as a principal software engineer who spent decades building, shipping, and scaling real production systems, I am absolutely thrilled to guide you through Chapter 29 of our massive 180-chapter journey. Today, we're tackling what is arguably the most powerful, ubiquitous concept in all of computer science, the graph.
Just to quickly ground ourselves in the overall map, we are currently deep into Module 2 Data Structures and Algorithms. We're bridging the gap from our previous chapters on trees right into the most flexible data structure you will ever write into your code.
Here's our architectural review for today. We'll deconstruct the anatomy of a graph, look at edge direction and weight, and break down 2 exact ways to store them in memory. Then, we'll evaluate the space-time trade-offs and prep for some real-world senior engineering interview questions. Let's kick things off with the anatomy of a graph. So, what actually is a graph? Well, you can think of it as a collection of vertices, often called nodes, connected by edges, which are the links. Now you might be thinking, hey, that sounds exactly like a tree, but here's the catch. A tree is just a highly restricted, special kind of graph. A graph completely drops those strict tree rules. There's no single root at the top. A vertex can connect to any number of others. You can have loops, cycles, and there's absolutely no forced top-to-bottom hierarchy. The crucial takeaway here is that a graph is simply things and the connections between them. It's the ultimate modeling tool.
Notice how, when you visualize it, there is literally no top node. You could easily loop from vertex A to B over to C and right back again. It's like a map of cities and roads. The cities are your dots, the roads are your lines, and you can drive around in loops all day long. Pretty much any network you can imagine in the real world works exactly like this.
Moving right along to our second section, edge direction and weight.
When you're architecting a system, choosing your direction is your absolute first decision. Graphs come in 2 main flavors here. In an undirected graph, edges go both ways equally. Think of a 2-way road, or a friendship. If I'm your friend, you're my friend. Simple, right? But in a directed graph, edges are strictly one way. An edge from A to B doesn't mean you can travel from B back to A. It's like a one-way street, or following someone on social media. You can follow them, but they definitely don't have to follow you back.
The second massive architectural decision is weight. In an unweighted graph, all connections are treated exactly the same. An edge simply exists or it doesn't. But in a weighted graph, every single edge carries a specific numeric cost, like literal distance in miles, time in milliseconds, or network bandwidth. And what's really fascinating here is that finding the shortest path doesn't just mean the fewest hops anymore, it means finding the path with the least total cost. This is exactly what's running under the hood of every GPS routing app you've ever used. All right, section 3, storing graphs. We've got the theory down, but how do we actually write this in code for a production environment? Our first and most common option is the adjacency list. This literally stores a list of connected vertices for each individual vertex. It's like giving every single node its own personal, highly curated contact book of direct neighbors. Because you only store the connections that actually exist, it is incredibly compact. For sparse graphs, where there are relatively few edges compared to a massive number of vertices, this is your absolute go-to standard. It saves a phenomenal amount of memory. On the flip side, we have the adjacency matrix. Think of this as a massive grid, a giant 2D array with a row and column for every single vertex in the entire graph. If there's a connection, you flip a 0 to a 1. Now, you want to know if node A connects to node C? Bam! Instant, constant time lookup. But there's a massive catch. It comes at the extremely steep cost of reserving memory for relationships that don't even exist. For sparse real-world data, it's a huge waste of RAM. Which naturally brings us to section 4, the space-time trade-offs. As senior engineers, we don't just pick data structures at random because they sound cool, right? We explicitly evaluate the space and time complexities. Here is the raw engineering trade-off. An adjacency list's space is strictly proportional to your vertices plus your edges. It's built for fast neighbor traversal. An adjacency matrix, however, hogs n-squared space for a full grid, just to give you that instant O1 direct connection check. You are literally trading an n-squared memory footprint for raw speed.
Finally, section 5, real-world modeling and interviews. Let's see how this all plays out when you're sitting in the hot seat at a top-tier tech company.
If you are interviewing for any serious back-end, systems, or full-stack role, you are almost guaranteed to hear some variation of this classic question. It's a great question because it tests if you actually understand the representation trade-off or if you just memorized a textbook.
So how do you nail it? Your model answer has to link your choice directly to graph sparsity and the specific operations you need to perform. Mention that the adjacency list is your default because space is proportional to vertices plus edges, which is perfect for sparse real-world data and fast traversals. Mention the matrix gives you O1 checks at the cost of n squared space. The trap people fall into here? Reciting the definitions but totally forgetting to mention that the adjacency list is the industry default simply because most real-world data happens to be sparse.
Once you breeze past the storage concepts, you'll hit the modeling hurdle. The interviewer will throw a scenario at you. Maybe it's a recommendation engine, maybe it's a build tool, and ask you to model it. This is where they test your ability to abstract complex systems. The absolute secret here? Define before you code. Literally say out loud, okay, these entities are my vertices and these relationships are my edges. Explicitly state if the graph needs to be directed or undirected, weighted or unweighted. The ultimate fatal trap is jumping straight into a whiteboard search algorithm before you've established the architecture. Because if your model is wrong, your algorithm doesn't matter. Finally, they might ask you for real-world examples. They want to see if you recognize the hidden architecture running everyday software engineering. Now, it's easy to say Google Maps or finding mutual friends. But you want to go deeper. Think about the web itself. Pages and hyperlinks form a massive directed graph. Think about your tooling. When your NPM package installer figures out dependency resolution, it's just traversing a directed graph. In fact, this exact same graph theory is what underpins the microservice topologies we'll design in Module 8 and the distributed ledgers we'll build in Module 9. Graphs are literally everywhere.
Look, if you take away just one single architectural rule of thumb from our explainer today, let it be this: default to the adjacency list for sparse data and traversals. Only consider the matrix for highly dense networks where instantaneous connection lookups are non-negotiable. Master that trade-off, and you're well on your way to engineering highly performant systems.
So, we've got our graph correctly modeled, weighted, directed, and efficiently stored in memory. We're perfectly set up for the next step. Coming up in Chapter 30, we're going to unleash breadth-first and depth-first search. But before we get there, I want you to ask yourself, if you were dropped into a massive, unmapped labyrinth, how would you write an algorithm to guarantee you check every single possible path without running in circles forever? Think about it, and I'll show you the code in our next explainer.
Welcome back, engineers. I'm a principal software engineer here at Durga Analytics, and today we're going to master the engineering reality of graph traversals. So, in our previous discussions, we figured out how to model real-world data as a graph. But, just having a graph sitting in memory, that's only useful if you can actually explore it. We need to be able to visit its vertices to answer critical real-world questions like, hey, can I reach this server from this one? Or what dependencies are tied to this specific module? In this explainer, we're going to break down the two fundamental ways to traverse a graph: breadth-first search and depth-first search. Now, just as a really quick reminder of our overall course structure, our programming and software engineering journey spans 9 comprehensive modules. We cover everything from developer tooling and core languages all the way to full-stack web, enterprise architecture, and blockchain. Right now, we're in Chapter 30, officially wrapping up Module 2, Data Structures and Algorithms. Today is all about transitioning from simply understanding these basic structures into deploying the actual traversals that bring them to life in your production code.
All right, here is our roadmap for today's explainer. We've got 6 parts. First, context and graph dangers. Second, BFS, level-by-level search. Third, DFS, going deep first. Fourth, trade-offs and comparisons. Fifth, the O of V plus C efficiency. And finally, number 6, real-world and interview prep. Let's get to it.
Okay, Section 1, Context and Graph Dangers. So why would a graph traversal risk running forever? Well, think about exploring a standard tree structure for a second. It's got a clear root, it's got leaves, pretty straightforward, right? But when we ship graph algorithms into a production environment, we face a very unique danger. Unlike a tree, a graph can have cycles, basically loops in the data. If you naively just follow edges without tracking where you've been, a cycle is going to trap your code in an infinite loop. Literally, it will just continuously revisit the exact same vertices over and over until it blows up your memory and takes down your entire production server at 3 a.m. Definitely not a fun PagerDuty call.
So how do we fix this? The absolutely crucial point here is that we must implement a visited set. This is your universal safety mechanism. In practice, this just means utilizing a hash set in Java or C++, or a simple set if you're writing Python, to record every single vertex you have already seen. Before you process any node, you check this set by making absolutely sure you never process a vertex twice. This simple mechanism makes your traversal totally safe and mathematically finite. Rule number 1. Graph traversals must always track visited vertices.
Moving on to Section 2, BFS, or level-by-level search. With our safety mechanism firmly in place, let's look at our first major traversal tool. This perfectly illustrates how breadth-first search, or BFS, explores in expanding rings. Starting right from your initial vertex, which we'll call level 0, it visits all immediate neighbors at level 1. Then it hits all of their unvisited neighbors at level 2, just radiating outward like a ripple in a pond. It completely exhausts everything one step away before it ever even looks at something 2 steps away. And because it explores in this strict order of distance in an unweighted graph, the very first time BFS reaches a target vertex, it is mathematically guaranteed to have found the absolute shortest path. It's brilliant. Now, under the hood, how do we actually enforce this strict level-by-level sweep in our code? Well, it's driven entirely by a queue. You know, a first in, first out, or FIFO structure. You enqueue your start vertex, and then you just repeatedly dequeue the front vertex, visit it, and enqueue its unvisited neighbors. Because a queue processes items in the exact order they were discovered, it naturally produces this outward, breadth-first expansion. Simple but incredibly effective.
All right, Section 3, DFS, or going deep first.
Having mastered how to go wide, let's flip the script and look at the exact opposite strategy. Here's how depth-first search, or DFS, behaves. Instead of expanding in those nice rings, DFS plunges as deep as humanly possible along a single trail. It goes from the start to a neighbor, then straight to that vertex's neighbor, and deeper still. It wanders exactly like a person trying to navigate a physical maze. It takes a passage until it hits an absolute dead end, and only then does it backtrack to the last junction to try the next unexplored branch.
Just as BFS relies on a queue, this deep exploration order is driven by a stack. This is a last in, first out, or LIFO approach. The most recently discovered vertex is always the one explored next, which forces the algorithm deep before it ever goes wide. Now, while you can absolutely use an explicit stack data structure in clean professional code, DFS is very commonly implemented by just leveraging your program's own call stack using recursion. Just a quick heads up though, if your graph is massively deep, you do run the risk of hitting a stack overflow error, so keep that in mind.
Let's check out Section 4, Trade-offs and Comparisons.
Listen, a software architect's job isn't just knowing the tools. It's knowing exactly when to choose one over the other based on system requirements. I really want to relentlessly reinforce this engineering trade-off for you. Both of these algorithms will visit everything that's reachable, but their exploration order dictates their utility. You can pair BFS with a queue to cast a wide net, specifically when distance or levels matter, like finding the shortest unweighted path. Conversely, you'll pair DFS with a stack or recursion to plunge deep for exhaustive exploration, existence checks, or cycle detection. It's the exact same core idea, but the underlying data structure you choose, queue versus stack, completely changes the behavior.
Next up, Section 5, the OV plus E efficiency.
When we're building real software systems, we absolutely have to consider scale. Despite their wildly different exploration strategies, both of these traversals share an incredibly efficient time complexity, big O of V plus E.
Let's break down why it's so efficient. Thanks to that visited set we talked about earlier, every single vertex is visited exactly one time, no exceptions. Furthermore, every edge is examined exactly once as we look at neighbors. Because of that, the total work is strictly proportional to the actual size of the graph itself, the vertices plus the edges. You really can't realistically get any faster than this when exploring an entire graph structure. They differ entirely in their exploration order, but definitely not in their total computational cost.
Finally, Section 6, Real-World and Interview Prep.
Let's connect these academic concepts back to the real world, both for building robust enterprise apps and, of course, for passing those high-stakes engineering interviews. When we ship this logic in production, these aren't just abstract ideas. BFS is the core engine powering features like GPS navigation, mapping connections on a social network backend, or even web crawlers that have to map out links level by level. Meanwhile, DFS, that is the absolute backbone of tools like dependency resolution in your package managers, making sure a deep dependency is built way before the module that actually relies on it. It's also the go-to for detecting cycles in those dependency trees.
Now, for interviews. Recognizing a traversal problem is honestly 90% of the solution. If a top tech company asks you for the shortest path in an unweighted graph, please do not reach for some complex weighted algorithm. Simply deploy BFS. Identify that it's unweighted, initialize your queue, set up your visited set, and start those expanding rings. Because it searches level by level, you have a solid mathematical guarantee that the very first time you hit your target, you have found the absolute shortest path. It's a real game changer to just know that off the top of your head. And with that, we have officially completed Module 2. You've progressed from basic linear structures to trees, balanced trees, heaps, and graphs. And now you possess the traversal techniques required to actually utilize them. You have a full arsenal of data structures and the exact means to efficiently explore them without getting trapped in infinite loops.
But, mastering structures is only half the battle. We've built the engine, sure, but what happens when you feed that engine millions of disorganized records? If you can't efficiently sort and optimize your data, your beautiful traversals will just crawl to a halt. So, how do the world's fastest systems actually organize their chaos? Join me in Module 3, starting with Chapter 31 to find out. See you there.
Hey everyone, welcome back. I'm your host, a principal software engineer here at Durga Analytics, and I am absolutely pumped to guide you through another mentoring session for our programming and software engineering track. Just to quickly anchor us, remember this track is a massive journey. We're talking 9 modules and 180 chapters total, taking you all the way from developer tooling and computer science foundations straight through core languages like Python, Java, C, and C++, into full-stack web, enterprise architecture, and eventually blockchain. Today, we are right in the thick of Module 2, Data Structures and Algorithms, specifically Chapter 31. We're diving deep into sorting algorithms and, crucially, their real-world trade-offs.
All right, so here's our game plan for this explainer. First, why sorting matters. Second, the ON squared trap. Third, production-grade sorts hitting ON log n. Fourth, stability and memory constraints. And finally, number 5, the sort-first pattern.
Let's jump right into Section 1. Why sorting matters.
Arranging items in order is easily one of the most foundational operations in all of computing. It sounds pretty basic, right? But mastering this actually sets the stage for basically everything else we build. We aren't just sorting to make the UI look pretty on a screen, it really serves 2 vital purposes. First off, humans and systems literally demand ordered data. Whether you're pulling up search results by relevance or checking your bank transactions by date, you expect to order. If you show users a randomized, chaotic list of data, they're going to think your app is totally broken. But the second reason, that's a real game changer for us as engineers. Sorted data unlocks dramatically faster algorithms down the line. If you've got an unsorted array and need to find something, well, you have to look at every single element. That's an O of n linear search. But if you sort that data first, you can use binary search, dropping that lookup time to a blazing fast O of log n. So it's an end in itself for users and a huge architectural setup step for us.
Okay, moving on to section 2, the O(n) squared trap.
Let's take a look at the intuitive, but honestly pretty dangerous, simple sorts you might be tempted to write from scratch when you first start coding. This brings us to insertion sort, and it's exactly like sorting a physical hand of playing cards. You pick up a new card, scan your hand, and just slide it right into the correct spot among the cards you've already arranged. Makes perfect logical sense, doesn't it? And for a handful of items, like, 10 or 20, it's actually super fast and effective, especially on data that's already mostly sorted. But think about trying to use that exact same sliding and shifting method to sort a deck of, say, 10,000 cards. The physical effort would be a total nightmare. And in software, that explosion in effort is a complete disaster for your system's compute resources.
And insertion sort isn't alone here. We've also got bubble sort. That's where you repeatedly walk through the list, swapping adjacent items that are out of order, which forces the larger items to literally bubble up to the end. Now, both of these algorithms are incredibly easy to understand, and they're conceptually beautiful when you're just a beginner. But they share a fatal flaw when it comes to large-scale production systems. They both involve comparing items against tons of others in a nested loop pattern. Because of those nested loops, they fall right into what we call the O(n) squared trap. Check out this quote we have here. Double the input, and the work roughly quadruples. This is the harsh reality of O(n) squared. If you have 100 users, sure, it's fast. 1,000 users, it's starting to get noticeably sluggish. But if your app goes viral and you hit 1 million users, your servers will basically melt down trying to sort that data. As your user base scales, your system performance just completely degrades. That is exactly why we absolutely cannot rely on these naive simple sorts for software that actually ships. Which brings us nicely to section 3, production sorts, specifically O of n log n.
To build real scalable enterprise software, we have to leap right over that trap and use the highly efficient sorts found in standard language libraries, whether you're working in Python, Java, C++, or JavaScript. Take a look at how this breaks down with the divide and conquer approach of merge sort. Instead of those nasty nested loops, merge sort takes the list and splits it entirely in half over and over again until you're just left with single elements. That splitting action, that gives you a logarithmic reduction, the log n part. Then it carefully merges those sorted halves back together into a whole. Touching each item per level during that merge gives you the n part. When you combine them, you achieve an optimal O(n) log n time complexity. It takes a massive, totally unmanageable problem and recursively slices it right down to size.
Now, right alongside merge sort, we have quicksort. Quicksort also uses divide and conquer, but it does it by picking a pivot value and then partitioning the list into items smaller than the pivot and items larger. As working engineers, look, you aren't going to be writing this code from scratch every day. Your standard library handles the implementation. But you absolutely have to know these trade-offs. Merge sort is going to give you guaranteed, highly reliable performance, but at the cost of needing extra memory to do all that merging. Quicksort, on the other hand, is incredibly fast in practice, often the absolute fastest, but it requires really careful pivot selection. Because in its absolute worst-case scenario, quicksort can actually degrade back into that O of n squared trap we just talked about. And that leads us to a really important mathematical boundary, O of n log n. For any algorithm out there that sorts by comparing items to each other, O of n log n is provably the absolute best possible worst-case time. It is literally the practical floor. When you use your language's standard library sort, it is operating at this O(n) log n floor. So, pro tip,
Don't waste your time trying to hunt down some magical, faster general-purpose comparison sort, because mathematically speaking, it just doesn't exist.
All right, let's pivot to Section 4, Stability and Memory Constraints.
Because hey, pure speed isn't the only thing that matters in enterprise architecture, right? Picking the exact right tool for your system usually hinges on two highly tested, real-world properties. The first is stability. A stable sort keeps equal items in their original relative order. So why does this actually matter in practice? Well, imagine you have a database of users, and it's already sorted alphabetically by last name. Now product management comes in and asks you to sort them by age. If you use a stable sort, like merge sort, all the 25-year-olds are grouped together. But within that group, they are still perfectly in alphabetical order from your previous sort. If you use an unstable sort, that secondary alphabetical order gets totally scrambled. When preserving existing ties is a hard business requirement, you absolutely must ensure your language is using a stable sort.
The second major constraint is memory. An in-place sort rearranges your data without needing any significant extra memory. So if you are programming embedded systems, dealing with massively huge datasets, or just operating under really strict memory limits, an in-place algorithm like quicksort becomes totally essential. Remember, merge sort requires duplicate arrays to process the merging, meaning it eats up extra memory. Quicksort mostly swaps items right where they already sit. Knowing how to match the algorithm to your actual hardware constraints, that is the absolute hallmark of a true senior engineer.
Which leads us to our final topic today, Section 5, the sort first pattern.
Honestly, this brings us to the highest value skill in this entire explainer, a concept that top tech companies are constantly testing for in technical interviews. We call it the sort first pattern. When you're faced with a messy problem, say finding duplicate users in a giant list, or finding the closest pair of financial transactions, or grouping similar items, the optimal engineering solution is almost always to just sort the data first. Step 1. Run your ON login sort. Boom! Now all your duplicates are sitting right next to each other. All the closest values are directly adjacent. Then, Step 2. Perform a single simple linear pass, which only costs O of n, to find exactly what you need. By paying that small upfront cost to sort the data, you turn a complex, tangled problem into a clean, highly efficient solution, and you completely dodge that naive ON squared trap.
Treating sorting as just some magical black box is a classic junior mistake. If you want to demonstrate real algorithmic maturity, you need to articulate these specific trade-offs when you're designing system architecture or sitting in an interview. Don't just randomly name-drop quicksort or merge sort. Tell them exactly why you'd choose one over the other. Discuss how stability affects the final order of tied items. Talk about memory constraints. And above all, when you're given a complex array problem, clearly voice your instinct to sort the data first before you try anything else.
So, we've arranged our data, we've bypassed the big performance traps, and we really understand our trade-offs. This sets up the perfect foundation for us, because in our next explainer for Chapter 32, we are going to leverage this exact sort of data to execute blazing fast binary searches. But before we get there, I want to leave you with a thought to ponder. If sorting our data unlocks searches in logarithmic time, what other seemingly impossible computational problems might just be one quick sort away from a totally trivial solution? Think about it. I'll see you in the next chapter.
Hey everyone, welcome back to our 180-chapter journey through programming and software engineering. I'm a principal engineer at Durga Analytics, and man, am I excited to jump into Chapter 32 with you today. If you've been following along, you know we're systematically building real, scalable systems from the ground up. And today we're tackling a concept that is just absolutely foundational to high-performance architecture. Just as a quick refresher on our overall roadmap, we are currently right here in Module 2, focusing on data structures and algorithms. Specifically, we're looking at the massive performance upgrade that is binary search. We're moving from developer tooling straight into the actual data structures you're going to use to build full-stack web apps, enterprise platforms, and yep, even blockchain ledgers. Here's our agenda for today's explainer. We'll start with our baseline, linear search. Then we'll check out the upgrade to binary search. After that, we'll unpack the math behind O log n, discuss the catch, which is sorted data, look beyond simple lookups, and finally wrap up with the real-world engineering impact. All right, let's get right into it with Section 1, Baseline Linear Search. So let's start with what we all already know, linear search. You just check every single item, one by one. It's super intuitive, right? It's usually the very first algorithm a developer writes. By definition, it has an O of n cost, meaning the time it takes scales directly with the number of items. Now, this is totally fine for small collections, but think about this. Imagine a web backend getting hammered with thousands of requests per second. An O of n scan through a million-item list, that will literally choke your application's responsiveness. It just doesn't scale. Which brings us to Section 2, the upgrade, binary search. To solve that bottleneck, we have to stop working hard and start working incredibly smart. If your data happens to be sorted, you can completely ditch that sluggish linear scan for a vastly better O-log-n approach. While linear search might work on any random, jumbled-up scramble of data, it falls apart at scale. Binary search, on the other hand, gives you blazing fast lookups, provided you meet its one core requirement. Think about it like playing a 1 to 100 number guessing game. If I ask you to guess my number, you wouldn't start at 1, then 2, then 3, you'd guess 50. If I say lower, boom, you instantly eliminate half the board. That's exactly what binary search does programmatically. You check the middle item, and if your target is smaller, you just throw away the entire right half. It's a massive engineering level up. Moving on to Section 3, the math. O log n. Okay, I really want you to let the sheer mathematical power of this halving process sink in. 20. That is the approximate maximum number of steps it takes to find absolutely anything in a sorted list of a million items. Compare that to up to 1 million checks with a linear search. If we scale that up to a massive enterprise database of 1 billion items, binary search only takes about 30 steps. 30! It's wild. This upgrade from O(n) to O log n is quite literally one of the cheapest and biggest wins we can implement when scaling real software systems. In the field, when you're designing database indexes or architecting back-end search features, capturing this logarithmic efficiency is exactly what separates junior coders from senior systems engineers. But there's always a catch. Section 4, the catch. Sorted data. As experienced engineers, we all know there are no free lunches, right? Applying binary search to unsorted data is a classic, catastrophic mistake. Discarding half the data is only safe when the order guarantees your target cannot possibly be in that half. If you chop an unsorted array in half, you might accidentally throw away the exact item you're desperately looking for. That leads to silent bugs and failed lookups in production, and nobody wants that. So here's the trade-off. Often, we architect our systems to intentionally pay the upfront sorting cost, specifically so that millions of subsequent database lookups can run in logarithmic time. Sorting data usually costs O(n) log n. But say you have an enterprise app where you insert data once and search it 1 million times. Paying that sorting tax up front is a massive architectural win. It's all about knowing your access patterns. Let's expand on this in Section 5, Beyond Lookups, Ordered Spaces. Let's move from a simple array lookup to a really powerful architectural pattern. You know, whenever you can ask a yes-no question where the answer flips at some threshold, you can binary search for that boundary. For instance, figuring out the exact minimum server capacity required to handle a peak load. You don't need a literal list of servers, you just test the middle value of your available capacity. If it crashes, you need more, so you have the upper space. If it holds, you can try less, having the lower space. It's an incredibly versatile way of thinking. Finally, let's bring it all home with Section 6, Real-World Engineering Impact. This isn't just theoretical computer science. This is exactly how top tech companies evaluate candidates. In interviews, demonstrating that you truly understand the O of N to O of log N upgrade and that sorted precondition is mandatory. Plus, interviewers love to watch you actually write the code for this. Why? Because calculating the exact midpoint and adjusting those search boundaries without triggering an annoying off-by-one error, well, that requires discipline, clean code, and extreme attention to detail. Mastering this gives you a durable capability to spot optimization opportunities that junior developers often just gloss right over. It connects straight back to our earlier lessons on Big O notation, and it directly informs how binary search trees operate under the hood. Recognizing this halving pattern isn't just a neat trick, it's a literal superpower in systems architecture. So we know why it's incredibly fast, and we know exactly when to use it. But as we wrap up this explainer, I want to leave you with an implementation challenge. How do you actually write the code to elegantly command a machine to break a problem in half over and over until it vanishes? That divide and conquer mechanism requires a completely different way of thinking about functions, and actually, that is exactly what we're going to conquer in Chapter 33 with Recursion. Thanks for hanging out with me today, and I'll see you in the next session. Welcome back to our ongoing explainer for the Programming and Software Engineering course. Today, we're tackling Chapter 33, Recursion and Divide and Conquer. I'll be your host today. I'm a principal software engineer over at Durga Analytics. And get ready because we are going to dive straight into the practical architecture of software to demystify one of the most powerful, yet honestly historically intimidating tools in any engineer's toolkit. Now at Durga Analytics, my team and I spend our days doing exactly what you're aiming to do, which is building, shipping, and scaling real software systems in production environments. Over the years, we've had the privilege of teaching thousands of developers how to build absolutely everything. We're talking the rock-bottom foundations like memory management and data structures, all the way up through the core languages, full-stack web applications, enterprise architecture, and even decentralized blockchain systems. Our core philosophy is simple. We focus on what actually works when you compile and deploy it to the real world. I just want to take a quick second to remind you of the massive 180-chapter journey we're on together in this course. We are traversing a strictly sequenced path across 9 complete modules. We start with Module 1 on developer tooling foundations, then Module 2 for data structures and algorithms. After that, it's deep dives with Module 3 for Python end-to-end, Module 4 for Java, Module 5 on C and C++, and Module 6 covering JavaScript and TypeScript. Finally, we scale up with Module 7 for full-stack development, Module 8 for application engineering, and Module 9 on blockchain mastery. It is a wildly comprehensive track, but always remember, everything we cover connects directly back to building code that actually ships. So where are we right now? We are deep into Module 2, Data Structures and Algorithms, specifically hitting Chapter 33. And you've actually already seen the fruits of today's topic. Think back a bit. When we covered merge sorts, splitting and combining in Chapter 31, binary search halving in Chapter 32, and tree traversal going deep in Chapter 30, every single one of those relied on recursion and divide and conquer. Today, we're finally going to learn how to wield the technique itself. Here's our agenda for today. 1. Demystifying recursion concepts. 2. The call stack engine. 3. Divide and conquer strategy. 4. Recursion versus iteration trade-offs. And 5. Real-world engineering and interviews. Let's get right into it. Section 1. Demystifying recursion concepts. Let's define what recursion actually means in the context of professional software engineering. At its core, recursion is simply when a function solves a problem by calling itself on a smaller version of that exact same problem. Now, I know that can sound a bit circular at first, but I promise you, it's not. As long as each recursive call works on something slightly smaller, and there's a simplest case that eventually stops the process, it works perfectly. It's an incredibly practical tool. It's essentially an engineer's way of saying, hey, to solve this massive thing, I'll just solve a slightly smaller version of it and build on that result. The absolutely crucial point to remember is that every correct recursive function has two distinct parts. First up is the base case. This is the simplest version of the problem. It's so small that the function can answer it directly without calling itself again. This is the brake pedal. It's what stops the recursion. Second is the recursive case. This breaks the problem down into a subproblem, calls the function on it, and uses that returned result. Let me be extremely clear here. Without a base case, your software simply never stops. It becomes an infinite loop, and your production servers will definitely not thank you for it. The base case is what makes the whole thing finite. Let's ground this with a really great real-life analogy from the source material. Imagine you're standing in a super long line of people, and you want to know your exact position in it. You ask the person right in front of you, hey, what's your position? Well, they don't know either, so they ask the person in front of them. This question passes all the way down the line until it hits the very first person. That first person is our base case. They can confidently say, I am first. My position is 1. Then that answer passes back up the chain. The second person adds 1 and says 2. The third adds 1 and says 3, rippling all the way back up to you. Each person solved a smaller version of the same problem and built on the answer from ahead. In code, this translates beautifully. If you're at the front, return 1. Else, return 1 plus whatever you get from asking the person in front. That's recursion in a nutshell. Moving on to section 2, the call stack engine. How does the computer physically keep track of all these nested questions under the hood? Well, it uses the call stack. We actually covered stacks back in chapter 24. Each time a function calls itself, the current execution is paused, its state gets pushed onto the call stack, and the new call begins. When a call finally hits that base case and finishes up, it gets popped off the stack, and the function call sitting right beneath it resumes with the returned result. Because a stack operates on a last-in, first-out, or LIFO principle, these calls unwind in the exact reverse order they were made. It is just standard, reliable stack bookkeeping. And this really shows the engine in action. Function 3 calls function 2, which gets pushed. Function 2 calls function 1, pushed again. Then function 1 hits the base case and stops. From there, the results unwind completely backwards, F1 to F2 to F3, popping off the stack one by one. But here is a massive warning for your production systems. If you forget to code that base case, the stack just grows forever. Eventually, you run completely out of allocated memory, and boom, you get the dreaded Stack Overflow crash. Section 3. Divide and Conquer Strategy. Now that we've got recursion figured out, let's see the overarching strategy that leverages it. This strategy is known as divide and conquer, and it relies on 3 very strict phases. Step 1. Divide the problem into smaller subproblems of the exact same type. Step 2, conquer each subproblem by solving it recursively, driving it right down to those easy-to-solve base cases. Step 3, combine those subproblem results into the final answer for the whole problem. Basically, you break it up, solve the smaller pieces, and put them all back together. What's really fascinating here is the raw power of this halving strategy when it comes to Big O. Merge sort divides a list in half, sorts each half recursively, and combines them. Because repeatedly having a dataset creates roughly log n levels, and combining them costs n, we get a highly efficient time complexity of O of n log n. Binary search is even leaner. It halves the data, but only bothers to follow the side that can actually contain the target. There's nothing to even combine. It just takes log n steps. Divide and conquer is the absolute secret sauce that takes incredibly inefficient O of n squared approaches and drops them down into highly efficient, scalable complexity classes. Section 4, Recursion versus Iteration Trade-offs. Let's put our principal engineer hats on and talk about the real world. As a working engineer, you never want to use a tool blindly. Recursion and iteration, meaning standard loops, can often solve the exact same problem. So the choice really comes down to code clarity versus system constraints. Recursion offers incredible clarity for self-similar branching data structures like trees. It reads so cleanly, assuming your depth remains pretty shallow, like log n. However, remember that call stack we just talked about? Every pending recursive call consumes physical stack space in memory. If your operation needs to go millions of levels deep, Recursion will blow up the stack and crash your program. In those specific deep cases, a standard iterative loop is absolutely the safer engineering choice. Section 5. Real-world engineering and interviews. Let's shift our focus to the finish line and talk application. How does mastering recursion and divide and conquer actually help you in the wild? Well, in real systems, you use this everywhere. Processing tree-shaped data like computer file systems, document object models, or abstract syntax trees, ASTs. All of these inherently demand recursive thinking. Furthermore, recursion is the foundational gateway to the upcoming capstone topics in this course. You simply cannot write efficient dynamic programming algorithms in Chapter 35 or backtracking algorithms in Chapter 38 without total fluency in recursion. And honestly, this is exactly what top tech companies are looking for in technical interviews. If they ask you how you'd approach a recursive solution, a model answer sounds just like this. I first identified the base case to ensure it will not overflow the stack. They are actively testing for structured thinking. They want to see that you prioritize termination conditions and that you strictly respect system depth constraints. Conversely, here are the traps that will instantly sink an interview. Trap 1, diving into writing code without defining the base case first. Trap 2, describing a divide and conquer approach but completely forgetting that the subproblems have to be combined back together at the end. And Trap 3, claiming recursion is always the most elegant solution while completely ignoring the real-world risk of a stack overflow. Listen closely on this one. A lack of awareness regarding stack limits is a massive red flag for any hiring manager looking for a reliable software engineer. So, we've seen how divide and conquer elegantly breaks complex problems down into manageable, combinable pieces. But it leaves us with a really interesting thought as we prepare for our next architectural pattern. What if, instead of meticulously dividing and conquering a problem, we just aggressively made the locally best choice at every single step along the way? Hold on to that thought, because that is exactly the strategy we are going to unpack in Chapter 34 on greedy algorithms. Thank you so much for joining me for this explainer, and I will see you in the next one.
Welcome back. I'm your host, and as a principal software engineer here at Durga Analytics, I am absolutely thrilled to guide you through the next step in our programming and software engineering journey. As a quick reminder, this course is a massive sequenced adventure across 9 modules and 180 chapters. We're moving all the way from Module 1's developer tooling foundations through our current home in Module 2 on data structures and algorithms. From here, we'll hit the core languages, Module 3 for Python, 4 for Java, 5 for C and C++, and 6 for JavaScript and TypeScript before scaling up into Module 7 for full-stack development, Module 8 for enterprise application engineering, and finally wrapping up with Module 9, blockchain mastery. Today, we are deep in Module 2, pivoting from our previous divide and conquer strategies in Chapter 33 straight into Chapter 34, greedy algorithms. Okay, let's dive right in.
Here's our roadmap for today's explainer. We'll start with the course map and core idea, look at when greedy works perfectly, explore the local optimum trap, define the greedy choice property, compare greedy versus dynamic programming, and wrap up with some crucial engineering and interview takeaways.
All right, Section 1, Course Map and Core Idea.
So, what exactly is a greedy algorithm? Simply put, it builds a solution step by step by making the locally optimal choice right now, without worrying about future consequences or backtracking. Now, what's really interesting here is that emphasis on right now. A greedy algorithm is remarkably fast and incredibly simple because it just grabs the best-looking option at the exact moment it's presented, and it never, ever reconsiders its past choices. As engineers writing code, you can see why this is appealing, right? Greedy algorithms are easy to write, They save precious CPU cycles, and when they actually work, they're often the most elegant solution available. But, as we're going to see, that simplicity comes with a massive caveat when it comes to shipping real production software.
To really visualize this, think of a hiker trying to reach the highest mountain in a massive mountain range. A purely greedy approach means our hiker always, without fail, takes a step in the steepest uphill direction available from their current footing. Now, this might quickly lead them up to a small local peak, but reaching the true highest peak in the entire range often requires walking downhill into a valley first, right? It requires a strategic retreat to access a much larger mountain. A greedy algorithm will literally never take that downhill step. This trap, where a locally best choice strands you at a merely local best rather than the global best, is exactly the risk we face when deploying these algorithms in our back-end systems.
Let's move on to Section 2, when greedy works perfectly.
Let's look at the happy path, where this strategy works flawlessly. We'll use a classic example, making change with the fewest possible coins. Imagine we have standard US coin values, 25, 10, 5, and 1, and we need to make 40 cents. Step 1, you take the largest coin that fits, which is 25. Step 2, you take the next largest that fits the remaining 15 cents, which is 10. Step 3, you take the remaining 5. With standard coin values, greedy works beautifully to find the minimum number of coins. You just repeatedly take the largest coin that fits, giving you an optimal 4-coin solution for 40. That's a 25, a 10, and a 5. In this case, the locally best choice of grabbing the biggest coin first directly leads to the globally best answer. It's simple, it's blazing fast, and it is 100% correct.
Another absolutely perfect application is interval scheduling. In real-world enterprise apps, you might be scheduling server tasks on an AWS backend or building an overlapping calendar event resolver. Your goal is to fit the most non-overlapping tasks into a given time frame. The greedy rule here is brilliantly simple. Always pick the available task that finishes earliest next. And the result? It provably gives the maximum number of tasks. The locally smart choice to free up your computing resources as early as possible actually builds the global optimum. When greedy works like this, it is genuinely lovely to code and incredibly efficient to scale in production.
But here is where things get a bit dangerous. Section 3, the local optimum trap.
Suppose we introduce a broken coin system with values 1, 3, and 4, and you need to make 6 using the fewest coins. Well, a greedy algorithm does what it does best. It grabs the largest coin that fits, which is the 4. That leaves 2, which then requires 2 1s. So greedy gives us 3 coins total, a 4, a 1, and a 1. But wait, the optimal answer is actually just 2 coins, a 3 plus a 3. Greedy's first choice, grabbing that initially appealing 4, looked great locally, but it led to a much worse overall result because it completely blocked the globally optimal path of using 2 3s. It's the exact same problem type, just slightly different coin values, and the greedy approach went from perfect to entirely wrong.
The danger here simply cannot be overstated for working developers. A wrong greedy solution often looks right, and it'll usually pass casual tests, only to fail spectacularly on edge cases. This is the essential trap, folks. Greedy's correctness is heavily dependent on the highly specific mathematical structure of a problem. You can never, ever assume it works just because the code is simple, looks elegant, and passes a few basic unit tests in your CI/CD pipeline. Shipping a plausible-looking but subtly wrong greedy algorithm can cause devastating silent failures in production resource allocation or compression systems. It can corrupt data or waste massive amounts of server resources without throwing a single explicit error.
So, how do we protect ourselves? Section 4, the greedy choice property.
To safely use a greedy approach, we look for what's formally called the greedy choice property. This is the core intuition that making the locally best choice never prevents you from reaching the globally best answer. Basically, the good choices never conflict with one another. In our working standard coin system, taking that 25-cent coin never blocked an optimal solution.
In interval scheduling, picking the earliest finishing task never blocked fitting the maximum tasks. The problem's underlying structure absolutely must guarantee that grabbing the local best option is always a mathematically safe step toward the optimal overall solution.
Our course text puts it perfectly, stating, "Do not trust a greedy solution until you have justified it or tested it against tricky cases, because greedy simplicity makes wrong answers dangerously plausible." The absolute core engineering discipline here is justification. Whether you write out a short logical proof in your pull request description, or you write rigorous edge case unit tests specifically designed to break it, we never ship greedy code on blind faith. This level of justification is exactly what separates a lucky guess from sound, professional software engineering.
Next up, Section 5, Greedy versus Dynamic Programming.
So when our justification fails, what's our reliable alternative? How do these two major optimization strategies compare? Well, a greedy algorithm is faster and simpler for sure, but it's only sometimes correct. Dynamic programming, on the other hand, requires more work because it considers combinations of choices, but it is reliably optimal even when local choices mislead you. When locally best choices lead you astray, just like they did in our broken coin system, your ultimate fallback is dynamic programming. It does the extra algorithmic heavy lifting to definitively find the true optimum. The engineering judgment we are building here today is knowing to reach for greedy when you can solidly justify it for the performance gains and having the wisdom to fall back to dynamic programming the moment local choices become deceptive.
Let's wrap this up with Section 6, Engineering and Interview Takeaways. If you are interviewing for top-tier engineering roles, greedy problems and greedy traps are incredibly common. Here are the meta skills you absolutely need. First, do not present greedy as generally correct. Make sure you communicate that its validity is purely problem-specific. Second, always have concrete failure examples ready in your back pocket, like our 1-3-4 coin example, to demonstrate to your interviewer that you understand its hard limits. Third, train yourself to spot problems that look greedy but actually aren't. And fourth, justify your simple solutions rigorously. In a high-stakes interview, spotting a problem that merely looks greedy and demonstrating the judgment and honesty to reject it and switch to dynamic programming is exactly the rigor that separates strong candidates from the rest. It shows you think like a seasoned architect, not just a junior coder writing the very first loop that pops into their head.
So, what's our final takeaway? Greedy is incredibly elegant when it's valid, but a dangerously quiet trap when it's not. Are you ready to master the ultimate fallback technique in Chapter 35? Now that we've learned to be deeply suspicious of simple solutions until they are rigorously justified, let's turn the page to Chapter 35 and master dynamic programming. That is the powerful technique that reliably solves the complex optimization problems that greedy simply cannot handle. Thanks for joining me today, and I will see you in the next explainer.
Welcome back, engineers, to this explainer, where we're going to strip away the intimidating reputation of dynamic programming and look at it simply for what it is, recursion with a memory. I'm your host, a principal software engineer here at Dorga Analytics, and over my career, I've spent decades building, shipping, and scaling real enterprise software systems. And honestly, if there's one algorithmic concept that separates junior developers from senior architects, it is absolutely this one. People hear dynamic programming and they freeze, but today we're going to demystify it. We're going to look at it not as some academic nightmare, but as a highly practical, beautifully elegant engineering tool. Now, as a quick reminder of our overall programming and software engineering journey, we are navigating across 9 core modules. We go all the way from developer tooling foundations into data structures, through core languages like Python, Java, C, and C++, right into JavaScript, full-stack development, enterprise app engineering, and finally, blockchain. Right now, we are deep into Module 2, Data Structures and Algorithms, landing squarely on Chapter 35. This builds directly on the recursion techniques we covered in Chapter 33 and the hash tables from Chapter 25, tying the whole shebang together. Here's our agenda for today. First, we'll cover the cost of repeated work. Second, the 2 conditions for DP. Third, memoization versus tabulation. Fourth, going from exponential to polynomial time. And finally, engineering and interview success. All right, jumping right into section 1, the cost of repeated work. We really need to identify the villain of naive recursion. To truly appreciate the solution here, we first have to recognize that villain. Think about a standard naive execution tree for calculating something as basic as the 5th Fibonacci number. You can instantly see this exponential O of 2 to the n waste happening in real time. The exact same subproblems, like calculating fib of 3 and fib of 2, are blindly recomputed again and again. To get fib of 5, your CPU is forced to compute fib of 3 twice and fib of 2 3 times. When you're writing production software, this doubling of redundant work makes naive recursion completely unusable for even moderate inputs. It's quite literally burning CPU cycles and destroying your application's performance. The insight to fix this is, well, almost embarrassingly simple. If you're solving the exact same subproblem repeatedly, just solve it once and remember the answer. Moving right along to section 2, the 2 conditions for DP, let's talk about the architectural fix. So we know the villain is repeated work, right? But a problem actually has to meet specific criteria for DP to work. The first condition is overlapping subproblems. This is exactly what makes caching, or remembering answers, pay off in the long run. If your problem breaks down into smaller subproblems, but those smaller subproblems never actually repeat, like an emerge sort, for example, then there is literally nothing to save. Plain divide and conquer is perfectly fine there. But if the identical smaller problems recur many times, like our Fibonacci example, you have overlapping subproblems. That's your first green light. The second condition is optimal substructure. This means those remembered subproblem answers can actually be combined into the final overarching solution you're trying to ship. Most optimization problems that ask you to find a best, least, or most value over various combinations have this exact structure. When both of these conditions hold, overlapping subproblems so that remembering helps, and optimal substructure so that the answers combine perfectly, dynamic programming applies. And let me tell you, it will dramatically transform your system's efficiency. Okay, section 3, memoization versus tabulation. Let's look at the implementation trade-offs in production. In the real world, engineering is always about trade-offs, and DP gives us 2 very distinct implementation paths. We can use memorization, which acts like local caching using those hash tables we learned about back in chapter 25, or we can use tabulation, which builds iteratively from the bottom up to safely avoid recursion depth risks. Let's break that down a bit. Memorization is top-down. You take the natural, elegant recursion, but you add a store, like a hash table or an array. Before computing a subproblem, you just check the store. If it's already there, boom, you return it instantly. This is highly intuitive because it barely changes your original recursive logic. However, because it relies on recursion, you absolutely run the risk of blowing up the call stack if the depth gets too crazy. Tabulation, on the other hand, flips the direction completely. It's bottom up. You start with the absolute smallest base cases and iteratively build a table up to your final answer. It requires no recursion whatsoever, meaning it's entirely stack safe and often a bit faster at runtime. As a senior engineer, choosing between top-down intuition and bottom-up stack safety is exactly the kind of architecture decision you're going to make every single day. Which brings us to section 4, exponential to polynomial time. This is the big payoff. The whole reason we care about this architecture is the sheer scale of CPU cycles saved. By never solving the same subproblem twice, dynamic programming literally shifts an intractable exponential brute force problem into a blazingly fast polynomial one. For our Fibonacci example, a single change, just adding a lookup table, collapses the exponential O of 2 to the n execution time straight down to linear O of n. Think about that for a second. It is the literal difference between a process taking millions of years to compute and returning an answer in milliseconds. It's a total game changer. Now, you might be wondering, okay, Fibonacci is great for theory, but what about real software? Well, when you're shipping this to production, these algorithms power massive enterprise features. When you look at a version control system like Git and see the diff between two files, that's a dynamic programming algorithm called longest common subsequence outwork. When your phone autocorrects a misspelled word, that's a DP algorithm calculating edit distance. Resource allocation, scheduling, sequence comparison, these are real-world optimization problems where a brute force exponential approach would completely crash your servers. Understanding DP means you ship efficient, scalable features instead of intractable, broken code. Finally, Section 5, Engineering and Interview Success. This is our Module 2 capstone. We really have to compare this to what we learned previously. Unlike the greedy algorithms from Chapter 34, which can sometimes fail when local choices mislead you, DP is your reliable, robust alternative to finding the true global optimum. If you make a locally optimal choice, and that choice blocks you from the true global optimum later on, a greedy algorithm is going to fail you. But by systematically storing and comparing overlapping subproblems, DP ensures you find the absolute best path, without having to blindly recalculate every single combination. Recognizing whether a problem requires sorting, binary search, a greedy approach, or DP, that is the core algorithmic judgment that separates an average coder from a lead engineer. Because it fundamentally converts impossible problems into efficient ones. Demonstrating genuine command over DP is one of the highest signal indicators of a strong engineering candidate. In technical interviews at top-tier companies, DP is famous for being tough, but honestly, it's only challenging if you try to just memorize solutions. If you approach it the way we just did, by articulating the subproblems, recognizing the overlapping nature, and explaining how a simple cache improves exponential time to polynomial time, you will strongly distinguish yourself from the pack. Now, while DP is a massive milestone, it doesn't quite wrap up our essential algorithms in Module 2. The big question now is, what specific patterns do top-tier interviewers look for next? We're going to find out as we continue Module 2 with Chapter 36, two-pointers and sliding window, which are absolute interview favorites. Until then, ask yourself, next time you write a recursive function, can you really afford to ship an exponential algorithm when a linear one is just a hash table away? Happy engineering, and I'll see you in the next explainer. Welcome back to another explainer in our programming and software engineering track. Just as a quick reminder of where we are, this is a massive 180-chapter journey across 9 modules, taking you all the way from developer tooling and computer science foundations right through the core languages, full-stack web, enterprise architecture, and eventually into blockchain. I'm your host, a principal software engineer over at Thurga Analytics, and today we are locked into Module 2, Data Structures and Algorithms. Specifically, we've arrived at Chapter 36, Two-Pointers and Sliding Window. Today is all about leveling up. We're going to talk about taking sluggish, brute force algorithms and mathematically compressing them into the kind of highly efficient, scalable software we actually ship in production. Here's a quick look at our roadmap for today. First, wasteful nested loops. Second, two-pointers and converging ends. Third, sliding window and moving ranges. Fourth, the complexity collapse. Fifth, spotting the cues. And finally, real-world and interview impact. Let's just dive right in. Section 1, wasteful nested loops. So there is a really stark contrast between how beginners write code and how senior engineers actually ship it at scale. When you're first starting out, you hit an array or a string problem, and the instinct is to just throw a brute force nested loop at it, right? You re-examine every possible pair or every single subrange. And as we talked about back in Chapter 21, that slams you right into an O of n squared execution time. For large inputs in massive enterprise systems, no way. That is just way too slow. But here's the secret. A lot of these problems have a hidden structure. If you can exploit that structure, you avoid re-examining data, and you completely collapse all that redundant work into a single O of n pass. It is honestly one of the absolute highest value skills you can build as an engineer. Which brings us to Section 2. Two-pointers, converging ends. Our very first architectural tool to achieve this optimization is the two-pointer technique. It's exactly what it sounds like. You use two coordinated position markers that move through your data in one single pass, without ever backtracking. Instead of firing up an inner loop from scratch every single time and wasting all those valuable CPU cycles, you just maintain these two markers. They move forward together, carrying enough context with them so you literally never have to look backward. To really visualize this, conceptually run the code in your head. The most classic use case for this pattern is on sorted data. You start one pointer at the very left edge, so your smallest value, and your second pointer way over on the right edge, your largest value, and then they just converge inward based on whatever condition you're checking. Imagine, for example, you're trying to find two numbers that hit a specific target sum.
Let's break down the exact mechanics. Step 1, park your pointers at the left and right ends. Step 2, check the sum of those two values. Step 3, and this is the magic part, if your sum is too small, you bump the left pointer to the right. You're stepping up to a larger value. If the sum is too big, you bump the right pointer to the left, stepping down. The elegance here is undeniable. Every single move safely and mathematically discards a value that absolutely cannot be part of the final answer. Because of that guarantee, your pointers always meet in O of n time. Quick pro tip here, you can also run two pointers in the same direction but at different speeds. We call that the fast and slow pointer trick, and it's a total game changer for detecting cycles in a linked list or doing in-place deduplication. But the core philosophy, one single efficient pass. All right, moving on to section 3, sliding window, moving ranges. Now we take that logic and adapt it for contiguous stretches of data using our second tool, the sliding window technique. You can think of this as a highly specialized two-pointer pattern. Imagine maintaining an actual window, a range with a left and a right edge that literally sweeps across your array. As it slides to the right, you just add the new element that's entering the window and you subtract the old element that's leaving. By expanding and shrinking like this, you examine each element O of 1 times instead of painfully rescanning every possible range. Depending on what your system requirements are, you're going to reach for one of two window types. You've got the fixed size window, which maintains a constant width. Say you need the maximum sum of exactly k consecutive elements. You just slide the window one step at a time, updating an O of 1 time per step. Then you have the variable size window. This one grows and shrinks dynamically based on a specific condition. A classic example is finding the longest substring with no repeated characters. The right edge keeps expanding to gobble up more data, and the moment you hit a duplicate and violate your condition, the left edge advances to shrink the window until it's valid again. Section 4. The complexity collapse. As platform engineers, we can't just know how to write this code, we have to understand exactly why the math behind it works. So why do both of these patterns achieve O of n linear time, even though we're constantly moving pointers and resizing window edges? It can definitely feel like there's a lot of jumping around happening. So how does that complexity actually collapse from quadratic to linear? Well, the secret engine humming under the hood is bounded forward movement. Your pointers only ever move forward. Because those edges never ever backtrack, you never redundantly rescan your data. Even with a flexible sliding window, the right edge sweeps across once, and the left edge just follows behind it. Each element gets visited a constant number of times, so your total work is strictly bounded by the length of the array. You're simply carrying your previous work forward instead of throwing it away and starting over. Let's look at Section 5, spotting the cues. Knowing these patterns is great, but spotting the cues for when to actually use them, that is a critical meta skill for both architecture design and high-stakes technical interviews. For the two-pointer pattern, your alarm bells should ring the exact moment you hear your data is already sorted, or if it can be sorted cheaply. It's also your go-to if you're tasked with finding a pair or triple with a specific property, if you're hunting for a target sum converging from both ends, or doing fast and slow traversal to spot a cycle. On the flip side, the sliding window pattern has its own set of very strong signals. If you're looking at a contiguous subarray or substring, if you're seeking the longest or shortest sequence, or maybe a maximum or minimum value in a range,
you absolutely want a window. Honestly, if the problem just uses the word consecutive, that is a massive flashing sign that a sliding window is your best bet. Section 6, Real-World and Interview Impact. Let's tie this all back to modern professional practice and getting your capstone portfolio ready. Spotting these cues quickly gives you a massive, repeatable edge in engineering interviews. And top tech companies love testing these patterns. Why? Because they perfectly mirror real-world systems engineering. When you're processing live data streams, running real-time analytics over time windows, or scanning network buffers, these are the exact ideas you use to keep your systems running at a snappy O of n linear time instead of crashing under O of n squared loads. Here's how this plays out in the real world. If you're asked for a target sum in a sorted array, they are explicitly testing the converging two-pointer pattern. The trap you have to avoid is defaulting to a nested loop or a hash table. A hash table works, sure, but it uses extra space, while the two-pointer approach does it in O of 1 constant space. If they ask for the longest substring without repeats, they want a variable sliding window. The trap there is rechecking every single possible substring, which completely tanks your performance. When you're documenting your model answers, explicitly talk about the complexity collapse. Showing a senior engineer exactly how you avoided those O of n squared traps by utilizing these patterns demonstrates real senior-level reasoning. I want to leave you with this core philosophy. Turning O of n squared into O of n is one of the most impactful and common improvements you can make, and these two patterns are the cleanest expression of it. Let that drive how you refactor and optimize code in the lab moving forward. Realizing that a brute force solution is just redoing work that a single forward pass could handle is a fundamental engineering instinct. Honestly, pulling that off is just one of the most satisfying moves in all of software engineering. And that brings us to the end of Chapter 36 on two-pointers and sliding windows. Practice spotting these cues in your lab exercises, focus heavily on that complexity collapse, and really internalize why O of n is so powerful. But before we sign off, I want to leave you with a question. What brute force O of n squared code is hiding in your current projects right now, just waiting to be collapsed into a single elegant pass? Think about that. Up next is Chapter 37, where we are going to dive back into graph data structures to master one of their most useful concepts, shortest path algorithms. I'll see you there.
Welcome back to our engineering journey. Today, we're tackling a problem that's literally at the heart of almost every real-world system you'll ever build: routing. We are in Chapter 37, and it's all about shortest paths.
I'm your host, a principal software engineer right here at Durga Analytics. You know, with decades of experience building, shipping, and scaling production systems, my main goal in this explainer is to really bridge that gap between computer science theory and real-world code. We're going to learn to engineer software exactly the way the professionals do. Just as a super quick reminder of our course roadmap, our sequence journey spans 9 core modules. That's 180 chapters in total. It takes you all the way from developer tooling and foundations, right through the core languages, and eventually up to full-stack web, enterprise architecture, and even a blockchain specialization.
But right now, you are here. We're zooming directly into Module 2, Data Structures and Algorithms, and specifically Chapter 37 on Shortest Paths. This chapter is absolutely crucial because it actually ties several of our earlier threats together into one of the most useful algorithms in all of computing. Here is our technical sprint for the day. The shortest path problem, unweighted graphs using BFS. When edges have different weights, Dijkstra, greedy meets heap. The engineering decision tree and wrap-up and next steps.
Part 1. The shortest path problem. Defining the engineering challenge.
So what are we actually trying to do here? Basically, it's finding the least cost route from one point to another through a network. In real-world software, whether you're building map navigation, routing network packets across the globe, optimizing supply chain logistics, or even programming game AI, you're constantly asking for the least cost route through a graph. Vertices are your places,
edges are your connections, and you need the absolute cheapest path between two of those vertices. Now, the keyword here is least cost, because as you'll see, cost can actually mean a lot of different things.
Part 2. Unweighted graphs using BFS. The simple fix.
In an unweighted graph, every single edge counts equally, so the shortest route simply means the fewest edges, or hops. And guess what? You actually already have the perfect tool for this in your tool belt, Breadth First Search, or BFS. BFS solves this naturally in O of V plus E time by exploring outward in these expanding rings of distance. Because it reaches nearer vertices before farther ones, the very first time BFS arrives at a vertex, it has literally taken the fewest possible edges to get there. It is incredibly efficient. When you're routing, say, internal API requests where every server hop is identical, BFS is your best friend for sure.
Part 3. When edges have different weights. The complexity.
Now think about the trap of just counting edges. Imagine a direct route from point A to point B with just one edge. Let's say that costs 100. But what if a two-edge route via an intermediate node C costs 10 on the first edge and 10 on the second, totaling only 20? Fewest edges does not always mean cheapest. The moment edges have varying weights, like milliseconds of latency between global data centers or toll fees on highways, BFS's fewest edges answer can be completely wrong for the least total cost. We need something a lot more powerful.
Part 4. Dijkstra, Greedy meets Heap. The engine of Dijkstra. To handle these non-negative weighted graphs, we use Dijkstra's algorithm. The way it finds the least total weight path is by keeping a tentative distance to every vertex. It starts them all at infinity, except the source, which is 0. It then repeatedly picks the unvisited vertex with the smallest known distance, finalizes it, and updates its neighbor's tentative distances if going through that vertex happens to be cheaper. You basically grow a settled region outward. And with non-negative weights, no cheaper route to a settled vertex can ever magically appear later.
You know, the real aha moment for system designers is realizing that Dijkstra is not magic. It is simply a greedy strategy implemented with a priority queue. This is exactly where multiple techniques you've learned in this course combine into a single, highly elegant solution.
Think about it. By combining the greedy choice, which is always settling the closest unvisited vertex next, with a priority queue, backed by a heap that pulls that closest vertex out efficiently in O log n time, we get an incredibly powerful engine for graph routing. You aren't scanning thousands of servers every single time. The priority queue just hands you the closest one instantly. This kind of synthesis of structures and strategies, that's exactly what distinguishes an engineer who truly understands how to scale their tools in production.
Part 5. The Engineering Decision Tree. Choosing your approach.
As a working engineer building features that real people rely on, you really need a quick mental model for this. Here is your architectural decision matrix. If the graph is unweighted, use BFS to find the fewest edges efficiently. If the graph is weighted but with non-negative weights, use Dijkstra to find the least total weight path. And if you happen to encounter negative weights, well, you need to step to a different algorithm entirely, like Bellman-Ford.
Let's actually expand on that last point for a second, because this is a super high signal interview answer at top tech companies. You absolutely must remember that Dijkstra's greedy assumption, the idea that once a vertex is settled, no cheaper path can ever appear, completely breaks down if negative edges exist. Why? Because a later negative edge could undercut a path you've already finalized. Knowing the boundaries of your tools is honestly just as important as knowing how to use them.
Part 6. Wrap-up and next steps. Capstone connection.
Shortest path problems are incredibly common, both in technical interviews and in real scaled production systems. Synthesizing these patterns is key. Recognizing that a routing problem is really just a graph problem. Knowing whether it calls for BFS or Dijkstra depending on the weights, and being able to explain that Dijkstra synthesizes greedy logic with a priority queue, well, that demonstrates the exact kind of deep understanding expected at top tech companies. Ultimately, comparing BFS and Dijkstra side by side really teaches us that selecting the right algorithm is simply about understanding the specific constraints of your problem domain. Is it unweighted? It counts fewest edges, expands in distance rings, runs in O of V plus E time? Go with BFS. Are there non-negative weights? It needs to count least total weight, greedily settles the closest, and needs a priority queue? Go with Dijkstra. But before we wrap up, consider this provocative thought. We now know exactly how to find the single optimal path through a network, right? But what if our software requires us to exhaustively, yet cleverly, explore every single possibility to find an answer, rather than just the absolute shortest route? That exact question sets the stage perfectly for our next chapter, Chapter 38, on backtracking, where we're going to dive headfirst into exploring those massive decision trees. Thank you so much for joining me on this explainer, and I'll see you in the next chapter as we continue to build out our problem-solving patterns.
Welcome back to our Explainer series. I'm your principal software engineer mentor here at Durga Analytics. Real quick, remember that this course, Programming and Software Engineering, is a massive 180-chapter journey. We go all the way from foundational dev tools up through core languages, full-stack web, enterprise architecture, and even a blockchain specialization across 9 modules. Today, we're diving into Chapter 38, Backtracking. You know, over my career, whether I was writing low-level C++ systems or architecting massive blockchain platforms, I've seen exactly why you have to master these fundamental algorithms before you try to scale a system to millions of users. So let's demystify one of the most powerful and honestly kind of misunderstood problem-solving patterns in our toolkit. Let's get right into it.
Here's our architectural roadmap for today's session. We'll start with the context, then explore the choice space, break down the try, explore, undo cycle, talk about pruning to make it all feasible, and finally, look at how backtracking shows up in real interviews.
So part 1, context, where we are in the track. Like we just talked about, we're on a sequence journey across 9 modules. We started with developer tooling, and we're heading toward things like full-stack JavaScript and enterprise apps. But right now, we are firmly in Module 02, Data Structures and Algorithms, specifically Chapter 38 of 180. Guys, this is literally the final major technique before our problem-solving capstone. Nailing this means you're one huge step closer to writing software that actually ships and scales in the real world. All right, moving on to Part 2, exploring the choice space, or the real-world problem.
In everyday software engineering, you're going to hit problems that genuinely require exploring a ton of different combinations. Maybe you're generating all possible arrangements or permutations of a dataset, or finding combinations that satisfy really strict constraints. Maybe you're building a solver for a conflict-free puzzle, or incrementally building up a partial solution. For these kinds of problems, there's just no clever mathematical formula or simple single-pass linear solution. You're faced with this massive branching set of choices, and the valid answer is just hidden somewhere inside that space. Backtracking is our systematic, professional-grade technique for exploring that massive space without completely crashing our servers.
Think of it like walking through a giant physical maze. You pick a path, right, and you walk down it as far as you possibly can. If you hit a dead end, you don't magically teleport back to the start. No, you just walk back to the last junction and try a different branch. You explore one path deeply, then you back up. In our code, this backing up is absolutely crucial. It means we're restoring our application state before we try the next available option. Which brings us to Part 3, the try, explore, undo cycle, the mechanical rhythm. Every single backtracking algorithm out there shares this super clear 3-step recursive cycle. Step 1, you try a choice. Say, placing a queen on a chessboard or picking an item to put in a subset. Step 2, you explore the consequences of that choice by recursing deeper into the problem. And then, Step 3, And listen, this is the most critical part. You undo the choice. You absolutely must unmutate your state so you can try the next option from that exact same starting point. It's this beautiful cycle that systematically walks the entire space without corrupting your data structures or causing messy memory leaks.
If you look at this, it brilliantly illustrates what's actually happening under the hood. Backtracking is essentially just depth-first search, good old DFS from back in Chapter 30, but applied to a decision space. Notice how every single node represents a partial solution, and each branch is a possible next choice. You go deep down one branch until you hit a dead end, or maybe a valid solution, and then you back up. Actually, when you see this visual connection, backtracking becomes way less mysterious. You already know the shape. It's just a tree traversal.
Now, take a look at how these classic textbook implementations play out. You're going to see this exact try, explore, undo pattern when you're generating permutations of a set, placing pieces in the n-queens puzzle so they don't attack each other, solving a maze, or even writing Sudoku solvers. But as a working engineer, I really want you to see the underlying pattern here. Solving a maze? That's just pathfinding. N-queens? That's resource allocation without conflicts. These might look like toy problems, but they're actively training your brain to handle complex, enterprise-level architecture constraints.
Okay, let's jump to part 4, pruning, making it feasible, which is really our core optimization.
Here's the thing. The search space in these problems is often astronomically huge, like exponential. If our code just blindly generated every single complete possibility before checking if it was actually valid, our application would just hang forever. That's where pruning rescues the algorithm. Pruning means abandoning a partial solution the literal second you realize it can't possibly lead to a valid answer. You just cut off that entire branch. By doing that early, we skip all the wasted computational work beneath it. Honestly, good pruning is the difference between a script that finishes in a few milliseconds and one that runs until the heat death of the universe.
And as a software architect, your job isn't just knowing how to write code. It's weighing trade-offs. Let's compare our tools. Backtracking is an exhaustive, worst-case exponential tool. It explores choice spaces. You should really only deploy it when the problem strictly requires it. On the other hand, if a problem has overlapping subproblems and an optimal substructure, you use dynamic programming. If picking a local optimum naturally leads to a global optimum, you use a greedy algorithm. Those are polynomial. The golden rule here, we never, ever force an exhaustive exponential search when a faster polynomial technique will get the job done.
Finally, part 5, backtracking in real interviews, signaling professional skill.
This interview cheat sheet right here highlights exactly what signals true senior-level skill to a hiring manager. When they ask you to generate permutations, they're testing your core structure. The biggest trap? Forgetting that crucial undo step and totally corrupting your state array. For the n-queens problem, they're testing your pruning concepts. Whatever you do, do not just call it brute force. And when they ask which tool to use, they are testing your engineering judgment. Knowing when not to use exhaustive search is just as important as knowing how to write one in the first place.
Guys, by mastering backtracking today, you have reached a massive milestone. Just look at this list. You now possess a complete professional-grade set of algorithmic tools in your toolkit. We've gone from fast lookups with hashing and pointers to binary search and sorting, divide and conquer, greedy algorithms, dynamic programming, graph traversals, and now disciplined, exhaustive search with backtracking. This is the exact foundation you need before we start building scalable, full-stack and blockchain applications later in the track.
Which brings us to the ultimate engineering test. You have the complete toolkit now. But when you're staring at a blank text editor in a high-pressure interview or fixing a massive production outage, can you quickly and accurately choose the right tool? The real difference between a junior coder and a senior architect isn't just knowing these algorithms, it's knowing exactly when to deploy them. In Chapter 39, Pattern Recognition for Interviews, we're going to learn exactly how to fluently choose among all these techniques when the pressure is on. So keep practicing that try, explore, undo cycle, and I'll see you in the next chapter.
Hey everyone, welcome to this explainer. I'm a principal software engineer at Duga Analytics, and today I am incredibly excited to take you through a pivotal masterclass in our programming and software engineering course. Today, we're bridging the ultimate gap. We are crossing that chasm between simply knowing your data structures and actually deploying them under pressure in a production environment.
Just to give you your bearings on our sequence journey across the 9 modules, you remember we kicked things off in Module 1 with developer tooling. Eventually, we're going to master core languages, full-stack web engineering, and push all the way through to Module 9's blockchain specialization. But right now, we are at the ultimate synthesis chapter of Module 2, Data Structures and Algorithms. This is Chapter 39. Pattern recognition for interviews, and it's where we literally tie everything together.
So, here is our game plan for today's playbook. 1. The real skill. 2. Mapping cues to techniques. 3. Structured problem-solving process. 4. Combining techniques and traps. And finally, 5. Acing interviews and capstone. Let's dive right in.
Section 1. The real skill. Let's completely redefine what problem-solving actually means in this industry.
Having spent decades building, shipping, and scaling real enterprise software systems, I'm going to let you in on a little industry secret. The hardest part of the job? It isn't writing the code. Honestly, Copilot can handle the syntax for you. The real challenge is recognizing exactly what code needs to be written when you're staring down an ambiguous problem. This paradigm shift is exactly what separates a junior developer hacking away at a keyboard from a senior engineer architecting a resilient solution. It's an absolutely vital meta skill. This crucial point is summed up perfectly by a quote right from our chapter. The hard part is usually not implementing a technique, it is recognizing which technique the problem calls for. You know, when you see a strong problem solver just breezing through a complex system architecture issue, they aren't necessarily smarter. They're just reading cues. They're recognizing shapes. Once you identify that a problem needs dynamic programming, the solution practically writes itself. And the best part? This is a completely learnable meta skill, not some rare innate talent.
Moving on to Section 2, Mapping Cues to Techniques. Let's get tactical. This tactical mapping is the immediate, actionable mental model you've got to have. When you hear the words fast lookup or have I seen this before, your brain should instantly scream hash table. In production, this is exactly how we handle front-end session caching or back-end frequency counting. What if the problem involves sorted data and finding a pair? Boom, that's the 2 pointers technique. Need a contiguous subarray? That's a sliding window, which is precisely how you'd handle real-time API rate limiting. You map the verbal cue directly to the data structure.
When you look at the complete map from this chapter, I highly advise you to internalize these triggers. Notice how a phrase like fewest steps unweighted maps immediately to breadth-first search, while least cost path, weighted, points straight to Dijkstra and a priority queue. Or if you hear cues about fewest, most, or optimal, combined with overlapping subproblems, you are firmly in dynamic programming territory. Memorizing these triggers dramatically reduces the time it takes to architect a solution, whether you're at a whiteboard interview or debugging a microservice at 2 a.m.
All right, Section 3, Structured Problem-Solving Process. The 5 essential steps you need.
Look, beyond just pattern matching, you need a psychological safety net to keep you from freezing up under pressure. We use a 5-step structured process. Step 1, clarify the inputs and edge cases. Step 2, example. Work a small example out by hand. Step 3, brute force. Just state the simplest, obvious, correct solution. Step 4, optimize, using that cue to technique map we just talked about. And Step 5, check. Always verify against those edge cases before you declare you're done.
Let me just pause on Step 3 for a second, because it's the one step engineers absolutely love to skip. Brute force gives you a guaranteed starting point and a baseline for true cost. Jumping straight to some clever pattern? Super dangerous.
Out in the real world, in enterprise software, we prioritize correctness over cleverness every single time. By stating the simplest brute force solution first, you guarantee you have a solid foundation that you can then optimize.
Section 4. Combining techniques and traps. Navigating the real complexity.
So, what happens when a problem is just too complex for a single technique? Well, hard, novel puzzles are usually just known tools combined together. You need to decompose them into subtasks. For example, processing contiguous ranges requires a sliding window, right? But simultaneously checking membership super fast inside that window requires a hash table. We actually already saw this in Chapter 37 with Dijkstra's algorithm, which combines a greedy strategy with a priority queue. You just have to break the monolith down into manageable parts. But you've got to beware of predictable traps. Disciplined engineering means checking preconditions and handling edge cases. The absolute most common trap? Premature optimization. Trying to write some slick ON algorithm before you even fully understand the brute force approach. It is literally like trying to build the roof before you've poured the foundation. Another massive trap is ignoring preconditions. You absolutely cannot use binary search on unsorted data, just like a greedy approach will fail completely if the greedy choice property isn't mathematically valid.
Section 5. Acing interviews and capstone. It's time to prove your skills.
Let's bring all this theory back down to immediate, real-world application. Top-tier companies love throwing this mock interview question at you. Walk me through how you approach a coding problem you have not seen before. The model answer maps perfectly back to our 5-step process. You tell them, well, first, I clarify inputs. Next, I work out a handwritten example. Then, I establish a brute force baseline. After that, I optimize by looking for structural cues, and finally, I check my work. That answer shows maturity, method, and reliability.
Here's another one to test your new reflex. An interviewer asks, you see a problem about the longest substring meeting some condition. First instinct, your answer should immediately be, longest contiguous substring triggers a sliding window response, likely giving us an ON solution. Boom! That proves you aren't just guessing, you are applying an engineered playbook. Do you see how this builds directly into your upcoming work? This exact pattern recognition process is the capstone skill. In Chapter 40, you're going to build a portfolio of solved problems. Every single entry must demonstrate this method: reading the problem, identifying the cue, selecting the technique, justifying it, and stating the complexity. It is the professional standard you are expected to meet moving forward.
Let me drive home a vital point from a practitioner's perspective. These are not just interview tricks. When you're on the job, debugging a microservice that keeps timing out, or fixing an enterprise web app that's buckling under load, performance bottlenecks are very often just wrong data structure problems. Mapping techniques correctly is exactly how you resolve real, expensive performance bugs in production code. You aren't just learning how to pass an interview here, you are learning how to engineer.
So I want to leave you with this thought. What hidden pattern will you uncover in your very next production bug? Is it going to be a missing hash table causing an O of n squared slowdown? Or maybe an unsorted array breaking your binary search? Take this meta skill and apply it on the job today. Mastering this is what makes you a true engineer. Thank you so much for joining me for this explainer, and I will see you next in Chapter 40, where we tackle the capstone itself.
Welcome to this explainer for Chapter 40 of our Programming and Software Engineering track. Today is a massive milestone, folks. We're officially wrapping up Module 2, and we're going to forge your entire data structures and algorithms foundation into one really powerful, career-ready deliverable. Let's get right to it. I'm your host, and as a principal software engineer here at Durga Analytics, I've spent decades doing the real work, building, shipping, and scaling actual production software. And, I've also interviewed countless candidates along the way. Just to ground us real quick in our sequence of 9 programs and 180 chapters, we kicked things off with developer tooling in Module 1, and now we're finishing up Module 2, Data Structures and Algorithms. Ahead of us, we've got end-to-end Python, Java, C and C++, JavaScript and TypeScript, full-stack web, enterprise application engineering, and finally, blockchain mastery. But today, right now, I'm going to show you exactly how to package the DSA skills you just learned into a tangible asset that hiring managers literally look for. Think of this capstone like an engineering architecture review. We're going to cover why you need a portfolio, the exact anatomy of a strong entry, how to cover your entire toolkit, building it step by step, using it to ace interviews, and then we'll wrap up the whole DSA module. Okay, Section 1. Why build a portfolio? Proving how you think. Here's the thing. When you sit across from me in a technical interview, or when you submit a pull request for a huge enterprise system, I don't just want to see that you can write code. Anyone can write code. I want to see how you think. In Module 1, you build a single application, which is awesome for showing you can swing a hammer. But DSA is totally different. Its true value is as a way of thinking. A curated, highly documented set of solved problems proves you know exactly when to use a hammer versus a drill, based on time and space complexity. It proves you understand trade-offs, which is honestly the whole essence of software architecture.
Moving to Section 2, Anatomy of a Strong Entry, the 5-part blueprint.
Out in the real world, a working block of code is practically useless without documentation. So every single entry in your portfolio needs to follow this strict 5-part blueprint to tell the story of your problem solving. Step 1 is the problem itself, clearly defining your inputs, outputs, and constraints. Step 2 is the approach. You've got to state the brute force method first, and then isolate your specific insight. Step 3 is technique and why. Justify why a specific pattern fits the problem's cues. Step 4 is complexity, meaning mapping out the real big O time and space cost. And Step 5, trade-offs. Honestly assess what your solution gives up. Like, are you trading memory for speed? This exact structure literally forces you to communicate like a senior engineer writing a design doc.
Section 3. Covering the entire toolkit. We're talking breadth over depth.
A truly strong engineering portfolio deliberately spans the whole toolkit to show off your raw breadth of pattern recognition. To prove you can handle absolutely any problem thrown your way, your capstone has to include at least one representative problem for each major technique you've picked up from chapters 21 through 39. So you need a hashing problem for fast lookups, a sliding window for a contiguous subarray, graph traversals, dynamic programming, backtracking, the whole shebang. Showing this breadth proves your foundation is rock solid.
Let's look at Section 4, Building Your Portfolio Step by Step, Flawless Execution.
Knowing what to include is one thing, right? But execution is everything. You're going to build this iteratively in 5 distinct stages. First, carefully choose your spanning problems. Second, apply the structured approach we learned in Chapter 39. Clarify with small examples, state the brute force, optimize it, and hit the edge cases. Third, write it all up using that 5-part template we just discussed. Fourth, verify your reasoning. You need to check your big O and preconditions like you're literally debugging production code. And finally, Step 5, review the whole deck for breadth. Your logic has to be so clear that another engineer can effortlessly follow it.
Let me put my engineering leader hat on for a second. I cannot stress this enough. Explaining the why behind your code is exactly what separates the junior coders from the senior engineers in enterprise environments. Your code tells me what the computer is doing, but your documentation tells me what you were thinking. All right, Section 5. Acing the technical interview. Deploying your asset. So let's look at the return on investment for all this hard work by deploying this asset in a real interview. A super common question is, tell me about a challenging problem you solved and how you approached it. When I ask this as an interviewer, I am directly testing your structured problem solving and your communication skills. Your absolute model answer here is to walk through a portfolio entry using that 5-part structure. The trap? Oh man. It's dumping the final, perfectly optimized code without taking me on the journey. A senior engineer desperately wants to hear the narrative of your brute force attempt and then the specific insight that led you to the optimized solution.
Next up, question 2. How do you decide which data structure or algorithm to use? This is the ultimate test of the exact pattern recognition skill your entire portfolio is designed to demonstrate.
Your model answer needs to explain how you read problem cues and map them to specific techniques. For instance, talk about how finding a contiguous range triggers a sliding window, or how overlapping subproblems instantly trigger dynamic programming for you. The trap to avoid is just instinctively naming a hash table because, well, it's your favorite tool. Don't do that. Show me the mapping logic.
And then we have question 3. How do you keep your problem-solving skills sharp? With this one, I'm really looking for professional habits, maturity, and your potential for long-term growth.
The perfect answer is to point out that you actively maintain and extend a solutions portfolio over time as a living document. Tell them you use it to rehearse pattern recognition. The massive trap here is implying that you just rely on leak code memorization. That's super brittle. Prove instead that your foundation is built on continual, documented practice.
Finally, Section 6, wrapping up the DSA module, the end of Program 2. It's time to step back for a second and just appreciate what you've built across the last 19 chapters. You started with the language of cost and Big O. You moved through core arrays, right into complex hierarchical and networked structures like trees and graphs. You mastered the essential algorithms, and finally, you tied it all together with complex problem-solving patterns. You literally have a complete professional-grade toolkit now.
Always keep our core philosophy in mind. DSA's value is a way of thinking, not one single app. This foundation is the shared language of computer science. It gives you a career-long capability to reason about computational cost, justify your technical architecture choices, and analyze the results like a true principal engineer.
Huge congratulations on completing Module 2 of the Programming and Software Engineering track. Your blueprint is ready, your toolkit is fully documented, and you know exactly how to leverage it. In our next chapter, Module 3, we're diving into end-to-end Python mastery. But before we write our first line of Python together, I want you to ask yourself something. Now that you can mathematically prove the absolute efficiency of your code, what kind of massive, highly scalable systems are you going to build with it? I'll see you in Module 3.